Oh, wow. Oh, that's right. So, okay, good morning. So I'm Aki Roberge of NASA's Goddard Space Flight Center, and I'm one of the two pre-formulation scientists in the HWO project office. Okay, so welcome to the last day of what I think has been a fantastic conference. I've found it absolutely wonderful. Yes, give a round of applause for everybody. To experience all the creativity and the enthusiasm, the last 3 days has been really good to experience. And there's more to come today. So, because I must, I will say, please fasten your seatbelts as we prepare for landing. And we will start with Adam Smercina speaking on resolved stellar populations in nearby galaxies. Adam, you are there. Great, thank you. All right, escape that. And you are here.
Can everybody hear me? Good. Great, that's pretty excellent. Thank you. All right, welcome to the final day of HWO 2025. Thanks for being here this morning. This has been a really, really excellent meeting, and I'm incredibly excited about all the science that HWO is going to enable. So today we're going to be talking about cosmic origins, and so I get to introduce this a little bit. This work was part of a science case with Tara Featheroff from UC Riverside. We're both part of the Stars and Stellar Populations sub-working group. And I'm a galaxy archaeologist, so that's what I'm going to be talking about today, and trying to understand the place of our galaxy, our Milky Way, in the vaster universe. So the nearby universe, or local volume, extends out to about 50 megaparsecs, or just under 200 million light years. And within this volume, there are about 15,000 known galaxies. And these galaxies literally come in all shapes and sizes. So as a reference, here are a sample of galaxies very similar in mass to our own Milky Way, within about a factor of 2. And you can just see all the diversity of structure and of star formation activity and central activity. And so we want to understand where this diversity comes from in galaxy properties. That's the Milky Way in the background. We think that one of the driving factors is the diversity in the evolutionary histories that galaxies experience. This is a simulation showing several billion years of the evolution of a Milky Way-like galaxy. You can see all of the mergers and interactions that it's experiencing over this time. And we think that, each and every galaxy experiences somewhat of a unique social life, much like we all do, over the 14 billion years of its existence. And so we think that these mergers and interactions are important, but how do we determine their impacts when they may have occurred billions of years ago? So one of the best ways that we can get at this is through studying their individual stars. So stars are long-lived. They are in large part independent of one another, right? They interact gravitationally, but not much else. And because of this, they encode the properties, environmental conditions of their birth sites, right? And so when we measure the colors and the brightnesses of stars, which can give us the temperature, something like temperature and luminosity, as I'm showing here, we can then infer the age and composition of stars. And I'm going to talk about this a little bit better here. I'm color-coding this model population by age. So this is a logarithmic scaling going from about 10 million years at the purple end up to about 10 billion years at the reddest end. And if I sort of peel back these layers, so I'm peeling back older and older layers, you can see how the structures in this HR, or observationally this would be a color magnitude diagram, help us infer age, at least in this case. So I'll flip back through once more. And so these populations of stars measured in galaxies, again, these are populations of individual stars rather than integrated measurements, allow us to reconstruct the evolutionary history of galaxies. And this is a very complementary but very distinct technique from some of the high redshift science that Steve Finkelstein told us about yesterday in his excellent talk. So instead of looking back sort of through redshift and through cosmic time to kind of infer some sort of bulk evolution of galaxies. This is looking at specific galaxies, right? Smaller numbers of individual case studies of galaxies, but we can infer the rate of star formation over their entire history, and in a bulk sense, in a general sense, the evolution of their chemical abundance, their abundance of heavy elements. And then we can ask the question, you know, certain features in these evolutionary histories, may they arise from mergers and interactions and other important events in galaxies' lives. So I want to talk about the legacy of studying the individual stars in nearby galaxies. It's not an easy measurement to make. And so before the Hubble Space Telescope, we really only had a couple galaxies that we could do this for. Now, this is the stellar mass of galaxies versus their distance along the x-axis. And this is for galaxies in the entire local volume. But I'm going to build up this plot slowly. So these Magellanic Clouds, these are the Milky Way's largest satellites. And this is really the furthest that we could reach before the launch of Hubble. So why is this? The answer is something we call stellar crowding. Many of you might also know it by a related term, confusion. So this is where stars are so dense on the detector that they blend together in a way that makes it very difficult, if not impossible, to separate them out and make measurements of the individual stars. This can be determined by the density, by the distance to the object, the resolution of your telescope. These are all factors. So this is a ground-based image on the left of the globular cluster M92. You can see lots of individual point sources, pointish sources in this image. But on the right is the Hubble Space Telescope image of the same region, and you can see many more individual points. Right? It's a deeper image, but also you might be able to tell, it's a very big screen, that many of those individual points on the left are actually blends of multiple points that pop out in the Hubble Space Telescope image. So Hubble really gave us access to multiple galaxies where we can study their individual stars, star-forming galaxies in our local group environment for the first time. And I think the best case of this is it allowed us to reach to our nearest neighbor, the Andromeda Galaxy, M31, which I'm showing a zoom in of this Hubble survey, the FAT survey here, and also its largest satellite, the Triangulum Galaxy M33. Now, Hubble may have given us access to the individual stars in these galaxies, but this was by no means easy, right? These are incredibly nearby galaxies, and so they're very big on the sky. So the Hubble field of view is very small compared to their optical extents. And so this took many hundreds, in fact, I think between the two, over 1,000 orbits of Hubble to get these images. And we've continued this work up until just very recently. This is a paper that came out by my colleague Zhuo Chen at the University of Washington just this year. And this is combining the original FAT survey with a Southern Treasury program to make the largest Hubble mosaic in history. Let me show you what that gets us, right? So this is, you know, this is the galaxy that kicked off the field of kind of galaxy archaeology and allows us to really dig into the evolution of this galaxy in detail for the first time. So these stars here on the left this is a map of stars that are about 4 billion years old in Andromeda. Just for reference, I'm going to give you some Earth timelines here to give context. So this is about the formation of the solar system. These are about 1 billion-year-old stars. This corresponds to about the development of multicellular life. These are much younger stars, about 200 million years old, corresponding to about the early Jurassic period. And these are the youngest stars, about 50 million years or less, or about the formation of the Himalayas. And you can just see the structural difference here with your eye. But we can use maps like this, and in fact, spatially resolved maps of the entire star formation history of Andromeda to infer how it's evolved, right? And the fact is that it's evolved very differently from our own Milky Way. The star formation history is very different. We think it's experienced a much more active and potentially a much more significant merger history than the Milky Way. And so if our nearest neighbor is so different from us, I think it really motivates studying a number of other galaxies, given this diversity that I showed at the beginning of the talk, to really say that we understand galaxy evolution. But this is an important first step. So JWST, it's a little bit higher resolution. It's able to beat down that stellar crowding a little bit better than Hubble was. So it's allowing us to extend these studies a little bit out into further out into the local universe. We're really just starting this process. The first example of one of these studies is going to be the Cibola survey that I'm leading of the starburst galaxy M82. This is really exciting. This is the first starburst galaxy, large starburst galaxy, I should say, that we've had access to its individually resolved stellar populations. So this is going to be very exciting. But this talks about HWO. So I just want to point out that we have not made it very far, even with these two outstanding space observatories, into this total local volume that I talked about at the beginning. So Hubble gets us out to about the edge of our local group. JWST gets us a little bit further out, right, into the local volume, properly, external galaxies. But what we really want is the rest, the vast majority of the rest of these 15,000 nearby galaxies, and this is what Habitable Worlds Observatory is going to be able to give us with its exquisite resolution. So I want to be clear, we can make these measurements for almost every single one of these 15,000 galaxies that you can see here. It's going to give us access to a level of diversity, fidelity, similar to our own Milky Way in a diversity of galaxies that is truly unprecedented. So we'll have major mergers, we'll have elliptical galaxies and lenticular galaxies. We'll even have different galaxy environments. So the Virgo cluster is that stripe of high density that you can see at about 16.5 megaparsecs. Totally doable with HWO, every galaxy in Virgo. So this is a pretty, I'm setting up a pretty incredible, I think, an incredible vision. But what do we actually need to do this transformative science with HWO? It's really not crazy. We need a high-resolution telescope, diffraction limited in the V-band or so. That's, I think, what we've been talking about all week. We need the pixels, right? We need this to be a well-sampled camera, NIQUA sampled preferably, to be able to distinguish these PSFs from one another in these crowded fields. And we need a good field of view. I think we argue in our science case that it needs to be a little bit bigger than what we had with Hubble. And the reason for this is that at these distances, the main bodies of these galaxies out in the local volume largely will fit into this 300 by 300 arcsecond field of view. And so doing these studies, unlike the FAT survey where we had to mosaic hundreds and hundreds of orbits of Hubble, we can do most of this science with kind of single fields. And so we'll have to go very deep, but we save a lot of time this way. And we need it to be panchromatic, right, which is another thing that we've all been talking about, right? UV to the infrared. This gives us access to all of the colors of stars in all of these different wavelengths, and allows us to distinguish age from metallicity, from reddening by dust. This is really important for this science. So if we build an observatory to these specifications, then we can turn all of these galaxies and hundreds or thousands more into fields of stars just like this. And I think this would be certainly the most transformative leap in my lifetime towards our understanding of galaxy evolution and understanding the place of our sun in our galaxy and our galaxy in the multitudes of galaxies that inhabit the cosmos. Thank you.
Okay, thank you, Adam. I think we have time for maybe just one quick question, if we have any in the room. Who's got the mic runners? Okay, John, go ahead.
Yeah. Hi, John Debus, Space Telescope Science Institute. So now that you're turning galaxies into individual stars, is there anything about stellar modeling, like atmospheres or stellar evolution that need to grow to match this sort of leap in millions and billions of stars all over the place?
It's a really good question. I think that the progress of stellar modeling and these observations will go hand in hand, right? I think that they're going to learn from each other. It's a really good point. I mean, we're sort of starting to think about the differences in how we model stars and the accuracy that gives us and how we're able to infer star formation histories, for example. So this is something that I'm actively working on with colleagues, thinking about bolometric corrections versus stellar tracks and how we can properly understand our uncertainties and things like this. But absolutely, I think we're going to do a lot of fundamental stellar astrophysics with these kind of data as well. I think the stellar IMF, right, being able to resolve individual stellar clusters in many of these galaxies is going to be really important. Yeah.
Thank you.
Thanks a lot.
Okay, and next we have Xinfeng Zhu speaking about spatially resolving the fundamental elements of reionization in galaxies. And let me get this one. Okay. Okay, thank you.
Okay, thank you. So hello everyone, I'm very glad to be here to talk about this science case, and thanks for the organizers to host such an amazing conference. And this work is in collaborating with the iPhoton sub-working group with their wonderful names here, you can see. So in the next 10 to 15 minutes, I will try to convince you why spatial resolution is very important for us to understand the cosmic reionization, and why we want the UV eye-field instrument to reach this goal. So the history, or the brief introduction, we have heard several times, for example, this week from Cody and Steven's talk, but I will just briefly talk about it. After Big Bang, the universe expands and cools, began filled with neutral hydrogen, which is called the dark age. Then the critical transition period happens when the first stars, galaxies, black holes, or planets formed. So then the ionizing photons they may escape will reionize the intergalactic medium around them. So this time marks the last phase transition of the universe, which is called the reionization era. So understanding cosmic reionization is also one of the key questions suggested by the Astro 2020 Decadal Survey. So here I show you how the reionization looks like in the current state-of-art simulations. In the left side, I show how the neutral hydrogen fraction looks like. So the blue bubbles are the regions gradually get reionized by the first stars and galaxies. And the right side shows the ionizing radiation field. While more and more ionizing photons escaped into the IGM, the radiation certainly get intense. So then the whole box, or the whole universe, get reionized after like redshift 6 to 5.5. So from current studies, the fundamental elements to reionization are the young massive star clusters. So basically here I show you how it looks like from our current view with JWST. So in the left side, I show the star clusters mirrored by the JWST, and you can see those star clusters look a bit stretched. This is because they are under a phenomenon called strong gravitational lensing, we also heard several times this week. So this is a redshift at redshift 10.2, and with age, universe age only around 500 million years old. And in the right side, I show the denuded image, so basically how it originally looked like in the universe. It's 5 bound star clusters within a small region of 30 parsecs. This is published in our Nature paper led by Angela Adamo. We also find that these star clusters have very blue UV slope, so they certainly have the potential to leak a lot of ionizing photons that contribute to the reionization at redshift 10. Okay, so let's take a closer look on one young massive star clusters. So this is also related to our science objectives I want to propose here. So the first thing we want to take a look at is the central star-forming region. They include a lot of young stars. So if we can resolve them, we can understand how much ionizing photons are produced and how much of them are escaping from the central regions. Then if we can resolve the interstellar medium around those star clusters, we can understand how the interstellar properties are. So for example, the gas metallicity, density, ionization, and dust extinction. Then finally, if we can resolve the geometry and the feedback mechanism, for example, winds and outflows around those star clusters, we are trying to understand these feedback mechanisms that might facilitate the escape of those ionizing photons. So given these pictures in mind, how do we resolve those star clusters? So there are mainly two categories of galaxies probe, to my point of view. So one are the strongly lensed galaxies, as I just showed in the introduction. So also in the figure here, we can see the lensed arcs can generally have a factor of 5 to 10 times lensing magnification, such that they will provide us with 5 to 10 times more spatial resolution just from nature. So this will certainly drop the blood pressure from our instrumental scientists by a factor of several. So, but however, these systems are a bit rare, so it's a bit difficult to build a statistical sample. Okay, but they are still very useful, and I show more of them through the whole life of the universe. Most of them are from JWST findings. So for example, from the left are redshift 10 ones when the universe is very young, and in the middle, redshift 6, then to cosmic new and redshift 2, then to the right are our current universe star clusters. So thanks for lensing, most of the times, the radius we find, or people find, are 1 to 100 parsecs, and they are usually very young and can produce a lot of ionizing photons. Okay, so the other way to resolve star clusters are certainly in the unlensed regular galaxies. So in this time, we will require higher spatial resolution, or instrumental spatial resolution, I would say. The good news is we have a lot of them, so this will allow us to build an unbiased statistical survey. So what specific spatial resolution I'm talking about here? So in the two figures, I show the angular resolution versus redshift for if we want to resolve the 100 parsec scales in star clusters. So in the left side is the case with lensing, the right side is without lensing. So you can see in the left side, if I assume a lensing magnification of 10, so then a 0.1 arcsecond angular resolution is already sufficient to resolve the 100 parsec scales. This is actually exactly what JWST is doing currently with its near-spec IFU instrument and NearCom. Then on the right side, we also have the without lensing case. It will become very challenging, as you can see. We will, for most of the redshift, except the very local universe, we will require 10 to 20 million arcseconds to resolve the star clusters. So this is certainly beyond the current scope of the JWST. And also, for your reference, for a 6-meter telescope, if we want to have the diffraction limit in the UV, it's actually 4 million arcseconds. So it's actually lower than what we require here. So I will return to the resolution later. So besides the spatial resolution, another challenge that prevents us to study the ionizing photon directly from high redshift universe is the high Z universe is really opaque. In the figure here, I show the IgM neutral fraction, which suggests that a lot of the ionizing photons will be directly absorbed by the neutral IgM above redshift 6, so we cannot directly see them on Earth. So what people find is to study the low Z analogs, which are the galaxies that are very similar to the high redshift ones, but they are at lower redshifts. So I really like Peter's talk on Monday, which are calling these low Z analogs are living fossils. So these living fossils, one of the typical studies are from the LZ-LCS survey, which are showing the right figure here. The gray and red points are all these low Z analogs. We have direct measurements of their ionizing photons. They certainly outnumbered the rest of the colorful points, which are from slightly higher redshifts. Okay, people have also been trying using current UV facilities to try to resolve those star clusters. And I show two cases here. First one is from Hero 11. People use HST's cosmic origin spectrograph to resolve the 3 star-forming regions in Hero 11. So even though it's only 2.5 arcsecond aperture, people can still find the escape fraction, the ionizing photon escape fraction from them are somewhat different. And in a subsequent NACOS program, we also find the ionizing photon escape fraction is dependent on the NIMA alpha features down to a 0.1 arcsecond aperture. So these two cases highlight the fact the ionizing photon is indeed highly spatially dependent, and we really need a UV IFU instrument to resolve it. Okay, so now it's time to summarize the instrument and requirements here. So I have 4 requirements put here. One, the spatial resolution. We will require 0.1 to 0.01 arcsecond, just depending on if we are studying the lensed or unlensed galaxies. Then the wavelength coverage, since we want to detect the ionizing photons, we want to detect rest frame 900 angstrom. Then depending on the redshift, it will be slightly longer wavelengths, maybe around 1,000 to 2,000 angstrom. Then the spectral resolution, we will have larger than 10,000 just to resolve the velocity distribution of the ISM. This is actually also mentioned in Cody Carr's talk on Tuesday for your more information here. So the sensitivity, we will have 10 to the minus 19. This is also from current studies of low Z analogs to detect 5% of the escape fraction at 2 sigma level. Combining all of this together, as many of the people mentioned this week, we want to have a high fidelity UV IFU instrument. So in this case, we will have a 3D spectral cube. In 2 of the dimensions, we will resolve the star clusters down to 100 or 10 parsec scales. And in the 3rd dimension, we will split the wavelengths into different maps, such that we can map the ionizing photon features and the UV spectral features. Okay, so how many of them do we need to resolve? In astronomy, we all know more data is better than less, so it's more about a comparison. So the state-of-the-art observations before the launch of HWO, I guesstimate we will have around tens of the lensed galaxies resolved. For the unlensed ones, due to the UV capability, I would say it will stay at 0 if no other UV instrument on sky. Then after launch of HWO, a substantial progress to breakthrough will be if we design unbiased statistical survey of a large sample of low Z analog galaxies to study. So these can be selected from a future Roman Space Telescope and UVAC surveys. So I will put my summary here and the scientific impacts, and also the 3D data cube only if we have the high fidelity UV IFU instrument. And if you want to learn more, you can scan this QR code for our archival submission. And thank you for listening. I'm happy to take any questions.
Oh, thank you, Xinfeng. Actually, I'm chair's privilege for, I'm going to start with a question. I'm wondering specifically what you mean by high fidelity when you describe this UV IFU. What do you mean by that exactly?
So what I mean is just a combination of all the requirements here. We need this high resolution, then the high spectral resolution, and high spatial resolution. And the wavelength coverage, certainly, if we want to focus on the low redshift ones, certainly they want to reach 900 angstrom. But I heard from several instrumental scientists it might be difficult to reach that. And certainly the sensitivity is there, yeah.
Okay, thank you. That clears it up. Do you have any, let's see, questions in the room? It's hard to see. Right there. Okay.
Hi, Elias Kovacs, Space Telescope Science Institute. You touched on it already, but I was wondering what kind of observations we should prioritize with James Webb and also with Roman to support this kind of science.
Yes, so there are several different things we can search. In Roman Space Telescope, actually, the wide field survey will already cover more lensed galaxies to study. So this can be the first step to go because we will understand the star cluster better because they are highly resolved. Even though, as I said, it is a bit biased because we are only probing the brightest clumps and we don't know the selection functions here. But then, if we can build a large sample at a lower redshift, certainly there are typical low redshift galaxies like green pea galaxies people know are analogs to the high redshift ones. If we can build an unbiased sample here to prepare for the future HW observation, it will be nice.
Thank you. Are there any online? Okay. Any other questions in the room? Up way back up there.
Thank you. I'm Shingo Kameda from Ryukyu University in Tokyo and JAXA. And this is a small question. So what is the request for the field of view?
Field of view, okay. Yeah, that's a good question I didn't mention. So for those resolved regions, they are usually not very large. For example, in the Hero 11, you can see the white circles are 2.5 arcsecond aperture by the HSC cost. So the whole view might be 5 to 10 arcsecond is certainly enough.
Good.
Not very large. No more pressure on the scientists, instrumental scientists.
Yes. Thank you. I think, let's see here. Actually, I think you were so good with your timing. I think there's one more question here. Yes.
Yeah, going back to the question, Steve McCandless, Johns Hopkins, going about the question about prioritization with JW. IFU studies to get dust maps of some of these green peas that have been observed with the low Z LCS would be extremely useful. And because dust has been found to be a correlated, anti-correlated with Lyman continuum escape.
Yeah, that's
Okay.
important.
All right, well, thank you very much. Let's thank both the speakers again. Okay. Okay, and now we were going to turn it over to Janice Lee from Space Telescope for a, what, for me anyway, highly anticipated panel on cosmic origin science. So, and I can do that.
Yeah.
These can be. Is that one? Is that one? This one. Marine technology.
Oh, Janice. I don't know. It's gone now. We'll never know.
There you go.
Oh, look, there. We didn't match our faces, you guys. We did it. We did it.
This is, as you can tell, this is going to be a
Very
very
early
interactive
astronomy.
panel. So this panel was originally called the Cosmic Origins Panel. As you can see on the screen, they renamed themselves the Astrophysics Beyond 100 Parsecs Panel. So we're going to start with brief introductions from our panelists. So we'll start from this side.
Hey, I'm Sarah Tuttle. I'm a professor at the University of Washington in Seattle. My areas of expertise are galaxy evolution from local galaxies through redshifts to 2 to 4, and the intergalactic and circumgalactic medium are things I'm very excited about. I also work in instrumentation, both ground-based and space-based spectroscopy in the optical and the ultraviolet. Wearing that hat, I will just briefly remind you, otherwise Cholet will find me, that we have a UV technology issue coming out in Janice very soon. It's a special issue. So if you have had lots of exciting questions about UV technology, you should keep your eyes out for that. I know there's also a special HWO Janice issue. I know less about that, so you'll have to ask a stranger. Really quickly, because we're trying to wake ourselves up, and maybe also you, if there are people in the audience who share scientific or technological interests with me, could you either stand up or raise your hand or do a little dance, whatever brings you the most joy? Yes, those are my, thank you. I'm so glad you're here.
So I'm Eric Burns. I'm a professor at Louisiana State University. Very broadly, I work on time domain and multi-messenger astrophysics. I sometimes pretend to be a physicist. And I work on, I forget the number, something like a dozen instrument teams for various satellites. So we're all asking you all, or each of us, if you share our scientific or technical interests, to please raise your hand. So for time domain and multi-messenger people, who are you? Thank you.
I like multi-messenger.
Hi, everyone. As I just said a few minutes ago, I'm Adam Smercina. I'm a Hubble Fellow at the Space Telescope Science Institute. And I'm broadly interested in nearby galaxy evolution, lots of stuff with resolved stars, as I just shared. Also the ISM in galaxies and their stellar halos and satellite galaxy populations. I've done a lot of work there as well. So show of hands, who's interested in stars and ISM and nearby galaxies? All right.
Hi, good morning. I'm Aisha Storchi Bergmann. I'm a professor at the Instituto de Física, Universidade Federal do Rio Grande do Sul, in the south of Brazil. There, since many years ago, I established a group, and I was kind of pioneer in the integral field studies of galaxies and AGN host galaxies with Gemini. And so this is why I'm very interested in the IFU in habitable worlds. And raise your hand who is interested in integral field. Well, a lot of people.
It's not usually a test, but that one was actually.
Okay.
My name is Alison Strom. I'm an assistant professor of physics and astronomy at Northwestern University. I'm a galaxy spectroscopist at what used to be called high redshift, so primarily redshift 2 to 3, but generally broadly interested in ISM conditions in galaxies across cosmic time. And I co-chair the ionizing photons and their history subworking group with Steve McCandless, who is in the audience today. And since we don't have an actual, I guess, what is now considered high redshift person on the panel, so I'll stand in for that as well. So galaxy chemistry, high redshift galaxies, do we have any takers? Okay, good. So raise your hand if you have any of our interests, like you share any of our interests, or any other interests that we haven't mentioned.
That you just know from
but
far.
beyond 100 parsecs. But look around, like it is your job to communicate to the rest of the community what HWO is going to do for us, and we want to spend the rest of the time kind of talking about that.
And thank you, too, to Alison for organizing the panel. It was a lot of work, thank you to all the organizers of the panels for investing quite a bit of effort to get people talking. Actually, I want to see the inverse. If you're not, be brave. If you're not interested in any of the things we've just mentioned, I mean, it tells me
We only listen, we don't judge.
no, but it tells me how much crosstalk. It tells us how much interaction between our very broad communities, the very broad communities that there are in this conference. So can you be brave? If you're outside these fields, can you raise your hand? Higher. That's not bad.
Alison, are you taking notes?
We should give them a round of applause. Thank you for being here. So what the panel wanted to do was to actually start off with questions rather than the panelists themselves talking. And then we do have some questions to then re-energize the conversation if there aren't any. But do you have questions in any of these areas represented by the panelists? Zemer. Zemer will start us off.
What's your favorite lowest wavelength UAV cutoff?
It's mean-spirited. Does someone want to take it first? I have too many allegiances here to answer that question. I would very much love for us to hit 100 nanometers comfortably. I'm not going to complain for anything under that. I think that it gets, at our current technology, right? We've had a lot of conversations about, and some interesting tensions between, are we open to new technologies for the next decade? Do we need everything locked down 6 weeks ago? Like, where are we at? Just sort of with the knowledge of where we are, I think 100 is feasible. And I think performance below 100 can improve as we develop real timelines and real instruments. If someone has a coding miracle they'd like to share and we're suddenly down to 50, I'm not saying no. That sounds great. More photons? Yes, thank you. That UV has historically been very tricky, though.
Anyone else on the panel want to comment?
I think that would satisfy a lot of the science goals that many of us are interested in. So as we just heard from Xinfeng, we really want to be able to look at the photospheres of massive stars, even in relatively nearby galaxies. So going down to 1,000 angstroms is very useful. But then it just gets easier, right? Because as you go out to higher redshifts, it gets to longer and longer wavelengths. But we want to be able to look at those massive stars over, the last 10 billion years of cosmic time.
I don't have a strong opinion, but 1,000 angstroms seems fine for me. Yeah, because I'm interested also in looking for starbursts around the AGM. And, I think the most important features are beyond 1,000, so it's okay for me.
Yeah, agreed. I don't do a lot of work in the far UV, but I think most of the chemistry we're interested in stars with spectroscopy is longwards of 1,000 angstroms, so that would probably be fine.
Far UV is an indicator of star formation. Yep.
That's the rumor.
So if you have questions or comments, leave your hands up because this is a large theater for the people to run around so we can get to you. Lee.
So a question for you about calibration. STS had a pretty complex lamp system, line lamps, broadband, flat field lamps. I don't hear a lot of people talking about the calibration requirements for all these different types of science and the implications to all these instruments. And I worry a little bit about, we're going to find some things that are going to be complex, and if we think about it early, it might be important. So I'm curious what your thoughts are in terms of, for your particular types of science, et cetera, what are some of the important calibration considerations that we should be thinking about now?
So one of the SCDDs is on the cosmological ladder, or avoiding it with just measuring Cepheids to 100 megaparsecs. And a discussion I'd like to have, which I'm not an expert in, is that you can also use Hab worlds to get very precise measurements of nearby type 1a in the UV, and you can then calibrate your type 1a to use the observations from Roman and Rubin, which at the redshifts are being measured at, that's what's corresponding to nearby UV. What the calibration requirements for that are, it depends how precise you want to be. You certainly would need under 1%. I don't think we need to get to the degree of anywhere near what Roman's doing, but I think that is a case where you do need reliable, absolute calibration across instruments. And we should find somebody to give us that number for that case.
Yeah, thanks. Jordi Miralda from Barcelona. So wanted to ask about something that I haven't seen being mentioned about these nearby galaxies, which is proper motions. The Hubble Space Telescope has started to do this with M31, M33, and so on, and I think it'll be so much better with HWO. So what should we be doing now to plan for these proper motions with a long baseline we're going to have? Also, things like intergalactic stars. The Rubin telescope will find probably RR Lyraes all over between us and Andromeda and all this space in the local group. How far can we bring that? Of course, we can measure great distances, proper motions, etc.
Yeah, so I'll take that to start here. I think that proper motions, that's a very interesting question. I think, first of all, doing proper motions beyond the local group with HWO is still going to be very challenging. But within the local group, as you say, for Andromeda or something, I think that could be a really exciting development. And I haven't thought a lot about this, but I think that the understanding our point spread function so that we have the highest precision imaging that we can get, specifically the time variability of the noise on the detectors and how that impacts the PSF. I think that will probably, allow us to start doing some of these very high precision measurements, like proper motions at the distance of Andromeda. And in terms of RR Lyrae, I think there was a talk yesterday in the parallel sessions by Deep Anand at STScI talking about just this. I don't know exactly how far out we're going to be able to do RR Lyrae. I think Deep was mentioning Cepheids out to 100 megaparsecs or something, which is a pretty large increase from what we're able to do now. So,
can I make a question to the audience? No. Okay.
Go ahead. Yes.
No, I'm interested in the coronagraph, and I wonder if there is experts in the room that talk about the possibility to use the coronagraph to cover an AGN that is bright, type 1 AGN, for us to see around it. So I wonder if somebody can answer this question. Oh, okay.
John, why don't you tell everybody what the answer is?
The answer is we would love AGM people to talk more about this.
Okay.
I'm John Debus. I'm at Space Telescope. I worked on the STS coronagraph for many years, and there's no technological reasons not to do it, right? Especially like with space telescopes, because usually people don't do it on the ground because AGNs are faint. You can't do all the cool corrections in the EO as easily with your coronagraph. So, but going to space, you don't have a lot of those restrictions. So I would say start thinking about science cases that can use even moderate contrast, right? Like with coronagraph, people talk about 10 to the minus 9, 10 to the minus 10, because that's absolutely what we need to do the planets. But we can do orders of magnitude less very, very easily. And so then our requirements for those kinds of lower contrast applications are usually a lot less stringent and more easy to do. So even though we talk about these insane contrasts that you probably don't care about, there's like orders of magnitude parameter space where you might care about it that are very, very helpful. And that's going to be true for Roman in some respects as well. Again, everyone is talking and focused on the technology, but the science capability is there for lower contrast applications. So if you have a low contrast application, even possibly for Roman, put a white paper in, right? Get the conversation started, because very rightfully so, there's a lot of technology focus and there's not a lot of conversation on science at this point. But if everything's working super well, then we as a community should absolutely be arguing for as many diverse applications as possible, because we don't want coronagraphs just to be thought of necessarily as, oh, you're just going to do the planets and that's going to take away all of our time, whatever, right? Like that's not what we're thinking necessarily. And so I mentioned on Slack in our little conversation, Bin Ren has a paper on a galaxy where he used STIS to do that.
Okay, yeah.
If you have other galaxies that have similar brightnesses or contrast requirements,
yeah, there are many
propose for
ones.
them. Yeah. So
Okay.
I know how to use STIS.
Okay.
So come talk to me. I'm happy to help anyone
Well.
write that kind of proposal, because I love to see that venerable 1990s coronagraph getting use. So yeah, absolutely.
Thank you very much.
A quick show of hands. How many people here would like to use the coronagraph for applications other than exoplanets? Look around. I feel like we've been having this conversation for a while, and I'm having deja vu from GPI, John. And Bruce has already left. So there's some kind of activation energy that we have to get over. But maybe we can really, really start the conversation in earnest here.
Okay.
Yeah, go ahead, Lee. Yes, John.
So I think we should talk about what wavelengths and field of view you're talking about. But from what I just heard, I mean, what STIS does is STIS just in the slit plane, instead of putting a slit, it puts this little thing that kind of sticks in there. You just need something that blocks the AGN in the image plane. If you want to do this in the UV, you're not going to do it in the coronagraph. You're going to do it in the UV instrument. You need to have an image plane. So then the question is, which of our instruments will have an accessible image plane with a mechanism that can put this thing in there, and then you can design whatever you want? And how many of these things do you want? NearCam has a series of coronagraphs, and you pick your field based on which one, so you don't necessarily need a mechanism. You just need access to an image plane at the right field point. So I think instead of thinking about how are we going to use a 10 to the 10th contrast coronagraph that works in the visible, you should tell us what wavelengths you want to do this, what kinds of shapes you want, and probably it's going to wind up in one of the UV instruments.
Hi, this is a question for all the panelists. What kind of modeling advances are going to be necessary in the next few years? I'm thinking particularly about SED fitting, but the question's open, because we're already playing catch up in some fields with JWST. So.
Yeah, so I've actually been thinking a fair amount about this. So those of you who are star-forming galaxy aficionados might know that we sometimes struggle to explain the helium-2 emission line recombination that we see in galaxies. And I just spent a few weeks talking to massive star modelers, and it feels like we actually have so many possible explanations for it that maybe we have too many helium-2 ionizing photons, but none of them are self-consistently included in stellar population synthesis models that also have synthetic spectra. And so I think what we need is for galaxy observers and stellar population modelers and stellar atmosphere and stellar evolution modelers to get together and try and come up with something that is self-consistent. Callum Hawcroft, who may or may not still be here, had a post on Starburst 99's recent upgrade, which is doing some important things, but there are many other things, X-ray binary accretion disks, strip stars, et cetera, that could be included that I think are important for explaining the UV emission that something like HWO would see.
I wish we had planted that question. I lied to all of you on Monday. I showed a web spectrum, and I told you that a line on top of that was tellurium. The truth is, we don't actually know what that line is. The best explanation we have is tellurium, but atomic spectroscopy is not complete in this regime. And it's actually the Webb observations which are driving atomic spectroscopists to go back and complete this work. So we have them excited with Webb. We got them excited with the neutron star merger in 2017. That event is mentioned in those planning documents in almost every field that I highlighted. So we need the atomic spectroscopists to do that. We need similar advances from nuclear and plasma. And we've begun discussions with a field called high energy density science, which was created by the Nuclear National Security Administration to emulate the simulations of nukes because they're not allowed to detonate them anymore, but they still have to make sure they work. So we're pulling their codes, which are 20 years ahead of ours, using it on flagship data. And what we're providing them in return is regimes in physics that cannot be created in terrestrial laboratories. So I think one of my main roles the next decade is going to these fields and tell them Hab World is going to make these observations. It's going to get exquisite ultraviolet spectroscopic measurements and identify a bunch of atomic lines. So you guys better be ready to tell us what they are. And I hope they'll listen.
I'll just mention briefly, SED fitting of individual stars is something that we've been thinking about more and more. So there's a tool called the Bayesian Extinction and Stellar Tool, the BEAST Python package developed at the Space Telescope by Carl Gordon and some other collaborators. But the panchromatic nature of HWO, at least what we've been talking about, right, UV through the infrared, the idea would be that you could individually fit the spectral energy distributions of not all of these stars, right? The faintest ones are going to be beyond that capability, but for the brightest ones, and be able to self-consistently derive ages, stellar temperatures, dust reddening towards individual stars, right? So you can make dust maps of entire galaxies and things. So I think there's a lot of computational, speed up that we need to do, and just developing this framework. But it's really exciting, right? I think we could do a lot with that kind of technique.
Okay, no other comments from Sarah or Thaisa on modeling? Okay. Aha.
Ross Belikov, NASA Ames. Before I ask my question, let me just mention that on the topic of coronagraphs and AGNs, Kevin Fogarty has thought a lot about this, and so he would be a good person to talk to. So my question is this. I don't know if this counts as astrophysics, but are there any ways in which HWO can search for life outside 100 parsecs or inform missions that would do that afterwards?
Well,
those people, Russ. Oh,
I have one thought.
I have a thought too.
Okay. My only thought, I don't think planetary science beyond lensing. Some people have thought about lensing, right, potentially. But, the types of data sets that I was talking about, especially for galaxies, say, within about 5 megaparsecs, we'd probably be detecting most of the solar mass stars in those galaxies, right? So you could think of, I don't know, in a century or a couple centuries time, right, having some map or catalog of solar-type stars in nearby galaxies. That's something that I think HWO could do.
So I think we have the potential to support the story for continued searches. one of the things I'm very excited about for HWO is the ability to map the circumgalactic medium and its connection to the interstellar medium to provide us with a much deeper understanding of how the elements are moving from kind of their cosmological scales to galaxies, to solar systems, and back out again. I think that when we think about how life has evolved in the universe, it's really important to understand how those elements might have been moving from relatively high redshifts, certainly places we don't expect to be getting biosignatures in many lifetimes, probably. Although future physicists, maybe they'll fix that for us. That would be great. But I think it does, when we're able to really understand the physics of how that gas is moving and how those elements are traveling, it then helps us gain insight into how, for example, habitable solar systems might be forming and what indicators we might be able to understand that don't require biosignatures, but maybe even give us information about like ISMs around solar systems. So we're able to kind of extend our view while we can't yet resolve planets.
I think we were talking a little bit yesterday about how the galactic environments would inform where to look.
Yep.
Does anybody want to comment on that?
Well, I mean, I think it's very interesting to think about the formation of the solar system in terms of redshift. So the solar system, the Earth formed at like 0.4 and change, right? And HWO collectively with the ELTs and JWST are letting us push down to Milky Way progenitor analogs from cosmic noon to today. And we'll be able to look then at spatially resolved galaxies at this time and ask the question, you know, what is different about the kinds of galaxies that might end up like the Milky Way, which we, you know, this is the one place we know supports life, versus other places that we see in the universe around us today.
Or even, you know, thinking about metallicity threshold for the formation of rocky planets. I mean, we have such different languages. We think of, you know, 12 plus log over h. I mean, I'm sure a fair fraction of this audience knows what that is, but, you know, many of our colleagues do not. But we don't even have some threshold where we think you need to be over a certain metallicity for rocky planets and disks to form. The timer was just reset. Are we done?
It's just counting up, it's fine. We can keep talking.
Just counting.
I know this is so much fun, but the next panel will also be a lot of fun. Let's give our panelists a round of applause. That modeling question was actually a really good plant for some of the things that the next panel will be talking about. And I'll hand it back over to the chair.
Oh, yes. Oh, sure. Thanks. Okay, yes. And next, Russ is going to moderate what I expect will be an exciting and potentially controversial panel on emerging technologies.
All right, hi everyone. Let me just bring up. Oops, that's not the right one. All right, let's talk about emerging technologies. Oh. I'll be here. Okay, let's talk about emerging technologies. We have a great lineup of world-class experts on several emerging technologies that could be relevant to HWO, ranging from AI to new methods in starlight suppression, to photonics, to detectors, and quantum sensing. And let me also thank Naseem for co-organizing this panel with me. And also, this panel was inspired in part by a workshop we held at NASA Ames in March. And a final report of this workshop is coming out, but you can also see a talk by Dominic Benford today at 5:30 on the 8th floor. So, the electric light bulb did not come from the continuous improvement of candles. And I think it's no exaggeration to say that all of NASA's flagship telescopes have had emerging technologies be game changers in some way. One good example of this is CCDs on Hubble, which were TRL-1 when Hubble was at about the same stage as HWO is right now. So what will be HWO's light bulb? One possibility is AI, and we have two world-class experts on AI here, Tanya Bedrax-Weiss, who is a senior director of Google Mind, and Andrew Vanderburg, faculty at Harvard. So, Tanya, could you tell us a little bit more about yourself, and what are the ways in which AI could be a game-changing technology for HWO, and what are the most impactful applications, potential applications that you see?
Hi, everyone. It's very nice to be here and learn a lot about astrophysics and the amazing work you're all doing towards HAB worlds. I have a small background I have a big background in AI, but I also have a small tenure at NASA Ames as well, hence why I'm here. I think AI, I hope most of you are very familiar with it. If not, please go familiarize yourself with it. I've been in AI for over 30 years. I think what we're seeing now since, I would say, 2017 is a totally different AI than we have seen in the past. Today, it's possible to use natural language to interface with AI, whereas in the past, you had to come up with formal representations, which were actually pretty fragile. And today, the fact that you're using natural language to interface with AI means that everyone can use AI. Now, AI is not a mature technology, certainly not TRL-6, but it is possibly one of the tools that you might consider using for a wide-ranging set of applications. It can speed up modeling, even for non-differentiable problems. You could probably use a very close approximation that is differentiable, and therefore use AI to speed up your predictions. AI technology is based on matrix multiplications, which I know most of you use in your day-to-day. So there's specialized hardware to speed up these matrix multiplications, which means that almost everything you do, you can use this specialized hardware for, which again, it's not TRL-6, but if we can get it there, I think it could be highly transformative. In particular, it can be a useful tool for doing science, hardware design, simulations, robotics, which was already mentioned earlier. So yeah, I'm here to hopefully push for AI. Thanks.
All right, thank you, Tanya. And Andrew, you've been quite successful in applying AI to astronomy. Can you tell us more about yourself, and what do you think are the most impactful ways in which AI could benefit HWO?
Yeah, so I'm really glad to be here, everyone. Although I must confess I'm a little bit of an imposter. I am an astronomer and don't necessarily have the same background in AI. But as Russ said, what I've been able to do is collaborate with AI experts and learn how to use these really powerful tools to improve our data analysis and improve our understanding of general astrophysics. I think that one of the really exciting things going forward is to change the way we use AI. So in particular, so far, when we apply AI to astronomy, it's often in the data side, in the post-processing. What if in the future, as we build an observatory with the capabilities of AI clear to us now, we can incorporate them into the flight? So you could imagine sending back compressed data using neural networks, or having some intelligent system to decide on the spacecraft what's important to send back if we're data rate limited. The possibilities are really endless, and it would be really exciting to build an observatory that's just fully immersed in this technology.
All right, thank you, Andrew. So shifting gears a little bit, let me introduce Susan Redmond from JPL and formerly from Princeton. Go Tigers! Susan is here to present emerging technologies in starlight suppression, and she's one of the smartest young people I know. So Susan, can you tell us more about yourself, and what are the main game-changing ways do you think that emerging technologies in starlight suppression could impact HWO?
Yeah, hi. So as Russ mentioned, I'm at JPL now. Throughout my grad school, I just wanted to mention, so I was very fortunate to be part of 2 different balloon telescopes, from CAD all the way through post-processing. And I got to see how we did like test flights, and then new technologies came out and we changed things, and then we did our science flight. And I got to see in real time kind of how those pivot moments can really help your science. So yeah, Hab Worlds is going to require these unprecedented levels of both starlight suppression and also starlight suppression stability. We heard a lot yesterday from our industry partners about these really stable technologies that we're working on, like these picometer level sensors and actuators. And any level of stability that they can gain on the observatory side is obviously going to help us a lot downstream. And also anything that we can do downstream to relax those requirements is going to speed up our development timeline. So some of the main things that I wanted to touch on is our mask manufacturing and mask technologies. So there's been a lot of work in metasurfaces, especially at the Micro Devices Lab at JPL, and also like things like black silicon and carbon nanotubes to make these grayscale apodizers. There's a picture there on the left of one of these grayscale apodizers that really help us deal with the diffraction effects from the segmented apertures. And if we can correct for those diffraction effects really effectively, then it really relaxes what type of coronagraph we can use and gives us a lot more options. I also wanted to mention, being able to do these, when we increase the size of our deformable mirrors and we increase the size of our dark zone, that makes computing a little bit more, a lot more difficult. If we wanted to, the typical Jacobians are going to be gigabytes, tens to hundreds of gigabytes. And being able to do that math on board is going to be important. And I think there's a great paper by Nick Belston about how much time it would take to just calculate the Jacobian with current rad-hard technology, and it's hundreds of hours. So advancing that is really going to help us out. And also just any sort of these real-time stabilization techniques at the focal plane. There's been a lot of work by Olivier Guyon about being able to use telemetry and post-processing to help us out in that regard, and really kind of approaching it from a big picture view.
All right, thank you, Susan. And representing photonics is Dan Sirbu. So Dan has recently become, and Dan is from NASA Ames, I should say. Dan has recently become what I think is one of the world's top experts on photonic coronagraphs, and he's the principal investigator of AstroPic. So Dan, could you tell us more about yourself and how photonics and photonic coronagraphs could potentially be a game changer for HWO?
Yeah, thank you, Russ. So I'm in the astrophysics branch at NASA Ames. Over the last couple of years, I'm the PI of AstroPic, which is a project that's building a photonic coronagraph. So I have here in my hand our prototype chip for AstroPic. So it's so small you can't see it. So there's a microscope picture blown up there showing the dimensions. So it's a chip that's 3 millimeters by 20 millimeters. And we're able to actually pack 2 different coronagraphs on this chip. So one of the game-changing aspects of photonics is really the miniaturization capability that it can provide for instrumentation, both for the coronagraph, but also other astrophotonic instrumentation. So it can help in terms of having small size, weight, and power requirements on the coronagraph instrument, but also other instrumentation. The photonic coronagraph is using a Mach-Zehnder interferometric mesh. So it uses Mach-Zehnder optical switches in order to interfere different portions of the pupil. And so this allows us to program that photonic mesh to perform any linear transformation between the input of the pupil to the output of the pupil. And so this gives us great flexibility. And to build on what Susan was saying earlier, this allows us to have wavefront sensing and control in a new way on the photonic chip, controlling the phase shifter elements on the photonic chip. So this gives a lot of reconfigurability in terms of tailoring the observations we can do with the coronagraph, but also other instrumentations we can think about to the current observation we're looking at. And I don't want to just talk about coronagraphs. We also, astrophotonics has the potential to change, so we can think of integrated spectrometers that can be put on the back end of the coronagraph, but also for general astrophysics. We can think of photonic lanterns that have been well represented at this conference. They're being adopted for ground-based telescopes, instrumentation, frequency combs. There's a lot of game-changing capabilities and technologies that photonics is bringing to the game.
All right, thank you, Dan. I can't believe we live in an age where we can carry a coronagraph in our pocket. Representing detectors and new advances in detectors, including quantum sensing, is Bernie Rauscher and from NASA Goddard. And I think that Bernie just might be the person who knows more about detectors than anyone else in the world. But maybe
I think I'll slink away on that one. Oh boy,
granted, I don't know. Granted, I don't know everyone in the world who works on detectors. But
okay. My name is Bernie Rauscher. I'm an astrophysicist at NASA Goddard. I am probably best known for detectors now. I led the JWST NearSpec detector team. I'm the detector scientist for JWST at NASA Goddard. I'm the senior detector scientist for the Roman Wide Field instrument, and I've been interested in developing and testing detectors for this application since it was known as the Terrestrial Planet Finder back in about 2003. So I'm going to be talking about single photon detectors today, which I think are kind of the breakthrough technology we need. Our position is all the way from the UV to the near infrared. Our position is fortunate in that there's a stable of very strong candidates that already exists. The challenge is going to be finding a way to get enough desirable properties into these detectors so that we have a small complement of detectors that we actually fly. You know, the challenge of counting photons and the visible has been solved by at least 3 or 4 technologies, I think some of which Shuli Nixad mentioned when she gave her talk. Some of these technologies are applicable in the UV with appropriate treatments of the surface, as I'm sure Shuli also discussed. They're the microchannel plates that are legacy from Hubble for the far UV. In the near infrared, efforts had been underway at adapting avalanche photodiode arrays for the ultra-low background conditions that exist here. The avalanche photodiode arrays, they're using a linear mode. We don't actually let them completely avalanche. Those have actually been used for years for LiDAR and in tactical sensing where they're optimized for high background applications. So we have a strong foundation to build on. We kind of just need to push enough of these technologies over the line so that we can comprehensively meet the requirements. And then I should also mention we also have low temperature detectors that are nearly perfect quantum sensors. Those include MKIDs, transition-ed sensor arrays, superconducting nanowire single photon detectors. There the position is also I think very strong. None of these things are TRL1. They're all at the threshold of mid TRL. But we would need a cryocooler, which is another technology innovation. I was also asked to address quantum sensing, and so I've started digging into that a few months ago for other reasons. The one and I've decided to interpret that broadly, because the one I really want to highlight is actually quantum computing. That's an area that is going to advance rapidly over the next 3 to 10 years, depending on who you talk to, driven by massive worldwide investment, billions of dollars per year. That's simply going to happen irrespective of what we do at NASA. So NASA just needs to be smart enough to maintain a presence in that community so that when the time comes, and I think it will, probably before HabWorlds launches, when we can do exciting things with quantum computers on the ground, maybe use them to improve our post-processing, or as a complement to lab astrophysics with simulating the chemistry of complex atmospheres. Others are going to pay for a lot of that, but for L2, NASA is kind of the only agency that goes to L2. The defense community, they're going to focus on low Earth orbit, so they might do some of the radiation hardening that's suitable for the relatively benign environment in LEO and geosynchronous orbits. And I'm not advocating this here because I think it's a very heavy lift, but if NASA ever wants a rad-hard quantum computer, whether it be for HabWorlds or what comes next, I think it's going to be on NASA to do the radiation hardening for L2. I don't think anybody else is going to do that. And then just two others briefly mentioned and then be quiet. Anything that on the quantum front that improves communications is great. More data on the ground, the more we can do. And then likewise, metrology. I wouldn't rule out advances in quantum metrology proving useful at some point.
Right. Thank you, Bernie. And you see what I mean. So next is John MacKenty, who is was an HST mission scientist and WIFPIC 3 co-lead, which counts as legendary in my book. So John, could you tell us a little bit more about yourself, and also what lessons can we take from, or rather, what are the greatest success stories of past infusions of emerging technologies into past flagships?
Okay, well, you asked me to talk about history a little bit instead of looking at the future, but maybe we learned something from history. I think there are a couple of useful lessons. The first one is to be bold. When Hubble was started, if you look at the early sketches, they actually had an astronaut in there changing plates when it was conceptual. But at the time that they proposed and selected instruments, I think the money would have bet on using a photocathode television tube type device. And in fact, ESA provided a very nice instrument, the faint object camera like that. But Jim Gunn and James Westphal proposed using CCDs, and that was pretty gutsy. At the time, the only CCD I think that had actually gotten on an astronomy telescope was the 100 by 100 pixel Fairchild device. Anyone who remembers the 300 by 500 pixel RCA devices that got on telescopes 4 or 5 years later remembers they weren't very calibratable, to put it kindly. They were quite a challenge to work with. But that investment paid off. It was not cheap. NASA, in fact, shared it between Hubble and Galileo to afford it, and wound up with 800 square devices that were, by that standard, pretty good. It took the QE of CCD QEs are 30 to 50 times higher than what we normally got from photographic plates, and 5 to 10 times better than a photocathode at the time. So it was a very big, dramatic step forward. As Hubble did multiple servicing missions, this is a plug for servicing missions, we were able to put better and better detectors on it. We sort of maxed out the QE, we expanded wavelength, lower read noise, things like that. The same pattern repeated with Iyer detectors. There weren't suitable Iyer detectors at the time, say in the early mid-'80s when Hubble's instruments were being built, but they started developing them. NASA put money into that. They eventually had 256 square devices from what's now Teledyne. They also, frankly, weren't that calibratable, but they were a big step forward. Fast forward a few years, we had devices, first 1K devices, there's a photo of that there. Those evolved into 2K devices that are the basis of Webb and Euclid, and the 4K devices, which Bernie and folks have worked on, that are absolutely spectacular. It's night and day how good these devices have gotten. A couple of thoughts about those. They were also collaborative. A lot of the push for building larger format devices didn't come out of NASA, it came out of the ground, particularly the late Don Hall in Hawaii, because people wanted them. Features in these detectors were added to make it possible to do AO work, which turned out to be really valuable for future missions. So the collaboration between other projects, I think, is something we should pay a lot of attention to. The last thing I'll say is it's very important for the astronomy community to engage with these things, to build their labs, characterize them. Frankly, with C3, we had to teach the people who were building them to measure them to our specs, because when we started, even for the CCDs, they couldn't come close to measuring what we wanted. And getting them out in the field to do science is very good. It's good for the careers of people working on them, but it's also good for really learning how they behave.
All right, great. Thank you, John. So following on that, let me ask the panelists, what advances do we expect in the near future, especially given that a lot of these emerging technologies are driven by massive industrial markets that have a very rapid rate of advancement. So let's start with Tanya. In AI, what do you think can we expect in terms of the most major advances driven by these massive industrial investments?
Gosh, AI is advancing, I would say, at an exponential pace, which means it's not linear, as you all know. So it's really hard to predict, 10 years from now, what it will be like. Because these tools are super easy to use today, you can interact with them easily, which means that they're becoming democratized. So almost every industry is starting to experiment. Starting to experiment is the key, right? So these technologies are not yet so mature that it's completely without challenges, and I think you'll hear about challenges shortly. But almost every industry is starting to experiment with them. What that means is that we are now seeing advances in, for example, material science, where we're discovering new materials, akin to the things and the advances you've heard of, hopefully, like protein folding. We're also making advances on things like material science. That means that maybe the materials you're considering today for coatings could be totally different tomorrow. You can have different requirements. Similarly in design of instruments, similarly in chip design and fabrication processes, all of these things, you can start seeing advances of how to improve, how to discover new ways of doing things, or how to accelerate processes, all the way also to the more obvious cases, like, for example, mission planning, planning observations, automatic control systems, actuator, et cetera. So I think my mission here is to just encourage you all to continue using these tools because they're advancing at an exponential rate. The fact that they don't work today for whatever it is you're trying to do doesn't mean that they won't work tomorrow. So please keep up with the state of the art so that we can see a great HabWorld's mission.
And Andrew, especially as an AI user, what do you think are the greatest challenges facing the application of AI to HWO?
Yeah, so I think that one of the biggest challenges with AI is learning when and how we can trust it. So I'm sure that many of you have seen, memes on the internet of AI failures. For example, making up court cases that have been submitted to a judge, or telling a user that they should eat rocks because it's healthy. This is not a terrible thing for many applications. If a person is told to eat rocks, hopefully they would have the common sense not to do that. But in astronomy, we really don't have that luxury. When I want for an AI system to tell me whether there's a planet around this star or not, so that I can decide whether to go and spend another 24 hours of HabWorld's time observing this object, I really want to be certain. So how can we figure out what is causing AI to make the predictions and the decisions and the outputs that it's making, and therefore decide for ourselves if it's trustworthy? So this is the goal of a field called explainable AI. And what we really want to do is try to build the tools and build the intuition and build the understanding of these tools, these really powerful technologies, to figure out how we as users can really debug and trust what they're saying. This is going to help us not just in astronomy, but also other fields. So one of the places that AI has huge promise is in medical imaging. AI systems are better than humans at identifying tumors or cancerous tissue in our bodies. But if an AI system took an image of me and told me that I had cancer and needed surgery tomorrow, I would not go and do that surgery without a human looking at it first. So understanding how we can trust AI in this situation in astronomy could help us in other industries as well.
Another area of massive industrial investments is photonics. So Dan, what do you think are the next greatest advances in photonics, and how can HWO leverage them?
Thank you, Russ. So the fact that I have a chip here that I can show you is partly driven by advancements from telecom industry. They're now able to manufacture chips, custom chips in low samples, low numbers, to our designs and specifications. So what we need to do is to keep developing these to meet the requirements for HWO, so that we do component design that's tailored to HWO's requirements. For chronographs, we have to reach contrast, bandwidth, and throughput. And we have to keep leveraging technologies and advancements that are being done for photonics in the same way that NASA was able to put CCDs on Hubble. We can also enable flexible, reconfigurable photonic chips on HWO.
Thank you, Dan. And Susan, what about you? What do you think are the greatest near-term advances in starlight suppression?
Yeah, so I think the metasurfaces is a big one. So they're sub-wavelength structures, and we can use them to potentially make really achromatic masks, and also potentially to correct for polarization aberrations, since we already know what those are. So we can even use it as just not a coronagraph, but just to put it on top of another optic to correct for all of those aberrations. And also, anything we can do with the appetizers to increase the throughput, because as Dan mentioned, throughput is, and I think also that we saw in Chris Stark's talk about yields, like throughput is a really big driver. And so correcting for these diffraction effects from the segmented aperture is something that we really need to do, but these appetizers also do decrease your overall throughput. So figuring out different appetization techniques and grayscale appetization techniques, that's where like the black silicon and the carbon nanotubes, and how we can apply those in a way that's clever and helps us in that regard, I think are two really exciting areas.
All right, thank you, Susan. So moving on to detectors, what do you think, Bernie, are the most impactful near-term advances in detectors and quantum sensing?
So for detectors, to be honest, our requirements are rather niche compared to the world at large. We want nearly perfect detectors that we read out extremely slowly, that we shoot to the harsh radiation environment at L2. And then finally, we want them to be cheap and available quickly in large numbers, ideally blister packed down at the Home Depot or something. Now, setting that aside, I think the one that's obviously really ripe is the quantum computing. As I said earlier, there's billions of investment pouring into that, lots of talented people. It'll be very surprising if we don't see breakthroughs there. The application to us at first is going to be on the ground. And for those who haven't tried, the algorithms are quite different. It's not going to be like programming a classical computer. You need to leverage the entanglement. You need to leverage the superposition of states. There are toolkits you can already use today. There's one for NVIDIA's CUDA-Q. So if somebody who's just entering the field and wanted to position themselves to be the masters of these algorithms, you could actually get started today on some of these quantum simulators, learning something about the algorithms and maybe developing them. So yeah, I think that's the one. The wave is going to happen, and it's just a matter of whether NASA decides to surf the wave or not. There will come a time when if we want to fly one to L2 for Hab Worlds or what comes next, we'll have to get serious about actually building rad hard ones. But for now, I think the wave is happening. The opportunity is there for those who want to learn to surf.
Great. And John, from going back to the historical perspective, what would you say is the most important lesson based on past experience in infusing technologies into past flagships?
I think part of it is to realize what gains. Be greedy. Astronomers are naturally kind of greedy, but to keep pushing on things, it's worth it. It's worth pushing on NASA to invest. It's worth building collaborations with industry and people in other fields who are developing things, look ahead a little bit. One thing I think is underappreciated is the systems approach to this. I mean, there are aspects of things, for example, if you have a detector that needs is more stable. You will not have to calibrate it as much. When we're doing missions that last for decades, the integral end of the field of the cost to the people to do those calibrations, if you have to recalibrate every week or every month, is truly non-trivial. It can exceed the cost of the detector. People are expensive. So looking at how it impacts the whole system, I mean, I think the astrophotonics potential is immense because we still wind up mass limited on a lot of these missions.
All right, great. Thank you, John. And with that, let me open the floor to questions from the audience. Sure, let's have a question from online.
So Sarah Steger asks, how does the fact that HWO will be serviceable impact the risk assessment for including emerging tech? In your opinions, does it provide more opportunities for something transformative on HWO, either on the initial mission or as a Gen 2 instrument after launch? How does this balance with the desire to advance the tech earlier with HWO than we did with previous missions?
I'll take a stab at the first answer. I think it opens up a huge opportunity, again, because we're seeing rapid advances in technology. I think one thing to keep in mind is not designing for it early can actually prevent some of the emerging technology from being deployed later when it's ready. So I think keeping an open mind, one of the examples was, for example, GPUs, right? I mentioned these highly specialized matrix multiplication computers. Being able to plan for them early and being able to do the groundwork to make sure that they're deployable at L2 is going to be key if we actually want to accelerate and have any promise of onboard AI even, or onboard rapid processing.
Let me just add to that in the history of Hubble. There was a decision that pained a lot of people in the community not to launch Hubble in its initial configuration with an infrared instrument. They put the money into CCDs. The infrared had to wait. It had to wait a little longer than they expected. Didn't launch to 97 instead of on the first servicing mission for reasons most everybody knows. But strategic choices have to be made. I mean, you're going to pick some things and not do other things. And how you make those decisions is actually probably pretty profound on the types of science the mission will do. And it comes back to the problem with all these missions. We're trying to predict the science we're going to do 2 or 3 decades into the future. And that's going to evolve. And if we're really lucky, we will evolve the technologies to hit the science we want to do at that time.
All right, I think we can go to the next question.
Okay, this is all very exciting. I especially like the prospect, thinking about how these things combine with each other and therefore multiply. And I'm sure that AI and quantum computing will revolutionize the way we operate the telescope in addition to the hardware we fly. But my concern is that we're not very well positioned to make good investments to leverage these technologies under NASA's current system of funding technology development. So I have a twofold question. One is, if I'm an enterprising young technologist in or outside the agency, and I would like to have the ability to fund myself or be funded to pursue one of these technologies with astrophysics applications, what should I do? And second, how would you advise our friends in the agency to get involved in these kinds of technologies and find their astrophysical applications sooner rather than later?
I can say one word to that. So our current project, our AstroPIC project, was funded by an STMD grant, early career initiative, that's actually encouraging new technologies. NASA needs to do more of that. It's a great program. Everyone that's a PI in that program really benefited from and really enjoys this program. It's providing mentorship, team building, and enabling us to look at new ways to develop technologies. So we need more of that.
That's great, but I'm thinking if you propose to something in SMD or Astro like SAT or APRA, they're probably going to say this is way too early to apply to habitable worlds. Those panels tend to be very conservative, so we need to find some way that we can finesse that problem.
I think you're asking 2 different questions. I think the answer to your first, in my view, is expand things like APRA and maybe other programs that do tolerate risk. I mean, APRA does not have any TRL limit on it. You can propose blue sky ideas to APRA. SAT, you're right, they tend to manage that tightly for mid-TRL. So if you're a PI, and I've been a PI of a couple of those, you report as if you're a project and you have explicit milestones for TRL. But the APRAs are much more flexible in terms of how you execute them. But part of it is also attitude. What you're talking about, the focus on TRL6 is something that comes up in missions. And this is why I think our last question was so important. A big flight project will require that all technologies be TRL6 by the preliminary design review, which is going to happen several years before you ship to the launch site. And they risk cancellation if they don't meet milestones like that. So they will be very, very strict about having their technology ready. Because we are serviceable, unlike for JWST, we're future-proof to a certain extent. You know, let's imagine there are wonderful breakthroughs on quantum computing, and there's a practical one in 3 years' time, and the military goes out and hardens one, and they launch one to low Earth orbit in 10 years' time. If NASA wants to pick up the ball, you know, even though you can never get it ready for mission PDR at that point, you can still aim for a servicing mission and perhaps have it.
So that's great questions and great answers. Unfortunately, we're out of time, but I encourage everyone to go and talk to these panelists afterwards. And thank you for joining. Let me just ask really quickly, how much does everyone love HWO? Thank you.
Okay, thank you all. Actually, one more round for all the panels and all the speakers from this session before we have break. Okay, thank you. And then back here at 10:50. Thank you.
Okay, I think this is on. Great. Okay, so I'm Meredith MacGregor. I will be chairing this last session. I'm an assistant professor here at Johns Hopkins University. I'm so excited that we were able to host you all for this amazing conference. Woohoo! So this is our last plenary session. So I see people trickling in, so I can do the airplane reference, like please return to your seats, stow your carry-on luggage, return your tray tables to the locked and upright position. Okay, so I will introduce our first speaker of the session. Scott Smith from Goddard Space Flight Center will be telling us about the HWO Road to Mission Concept Review.
Thank you, Meredith. Hello, can you hear me? Yeah, excellent. So we're trying to land our airplane today, but it's not our final destination. So I'm Scott Smith. I am the project manager, and I will first say that this is a huge contribution from a lot of people on the team. This is not just my slides. So when setting a goal and setting an objective, it's important to visualize what your endpoint is going to go. And I want to share our vision with you. So with Hubble here, it's more than a telescope. It's the byproduct of an incredible team. And we have people on our team that supported Hubble. We have scientists and engineers, scientists that work their days getting their PhDs. We have engineers that spent many nights in the lab building the instruments. And we also have the technology, the UV coatings and instruments. And we have servicing. And speaking of servicing, we have John Grunsfeld servicing Hubble here. And John's part of our team because we want to make sure that servicing is right. And just like Hubble gets better with every servicing mission, we also get better at doing flagship missions. And HWO will also be building off of the James Webb Space Telescope. So our scientists and engineers did an amazing job there as well, pushing the boundaries of technology. And on the left, we have the instruments where I supported and with the larger team, and we have the large segmented telescope as well. And from Webb, we're pulling wavefront sensing and control. We're pulling from our micro-shutter arrays. We're pulling from large deployable systems, and so many more. And no one will deny the challenges that Webb had along the way. And we have lesson learned written in journal articles, and it's one thing to read those journal articles, but it's another to have the scar tissue because you lived it. And we have those people on our team because we continue to get better at large flagship missions. We're also pulling from the Roman team. We're starting with the Roman team, and as Roman finishes, we're going to be capturing more of these people. The Roman team has ingrained in their DNA how to keep a project on cost and schedule. And we're going to capture that and have that as part of our team as well. So I love this photo on the left. It's a conglomerate of a telescope and the world's most stable telescope and the world's best coronagraph. We have the wide field instrument that's behind the coronagraph. You can't see it, but it's there. And we have the instrument carrier that bolts everything together, and they were all built in different institutions. And we brought them together and bolted them all together within 100 microns of accuracy. And on the right, this picture is maybe about a week old, where we have Roman going into the TVAC chamber. And the team has done a phenomenal job of holding to cost and schedule as we go from putting all the pieces together to going into TVAC chamber. And we are going to capture that on HWO, that vigor. And HWO will also pull from technologies like integrated modeling and deformable mirrors, and of course the stable telescope and the coronagraph. But in addition to all of our flagships, we're also pulling from others. We're pulling from the many studies of TPF and At Last and LUVOIR and HabEx and many others. And I must say, this is an incredible team that we have together. Now, I do want to talk a little bit about a project lifecycle because we're talking about, our road to mission concept review. So this is the traditional project lifecycle, and we are at the beginning of the beginning. We are at the pre-formulation concept stage, and we're working towards our mission concept review. One thing I want to point out is traditionally, technology development occurs in phase A. But we're doing that different. We're pulling that left because we know that we want to retire that risk. Broadly, a project can be broken down into 3 parts where we plan, execute, and operate. And the execute phase is where things become complicated, where challenges are more expensive to fix. And the way that you execute perfectly or well is the planning. And right now, in the planning phase is where we need to focus so that we can execute. We want to think slow during the planning phase so that we can act fast during the execute. So how are we doing this? We're exploring the trade space, but more broadly, we're exploring design, we're doing analysis, and we repeat. So we are starting with all of the earlier studies. And we started with EACs 1, 2, and 3. And from here, our designers focused on each one, capturing the energy and the designs of each one. And you can start to see how they start to deviate. And once our designers had pencils down, we handed this off to our integrated modeling team and our scientists and our industry partners. And then they were able to tell us all of the things about how stable the telescope is and what is our yield going to be, and if this is manufacturable. And then from there, we're able to capture what all of this feedback and focus in on EAC 4 and 5. And on EAC 4 and 5, one thing you'll notice is that our apertures got larger for the primary mirror, because we know through that feedback that we want less miracles on the instruments. EAC 4 is 6.5 meters, which is in family with Webb. But I want to point out that it has twice the collecting area because of how we've designed the optical system. And EAC 5, we're still refining, but it's over 8.5. So I want to dive into the mission concept review a little bit more, because I know everybody loves their NASA documents. But broadly, the mission concept review is to evaluate our feasibility and determine whether the concept maturity is ready to enter phase A. That's very broad. So let's dive into 1001A a little bit more. So 1001A, this is one of our documents that defines how the mission concept review is. But let's start with the science, because it all starts with the science. And from the science, we get our mission objectives. And the mission objective is we want to find exo-Earths. And we want to answer the question, are we alone? And from the mission architecture, or from the mission objectives, we get a system architecture where we say we need a coronagraph and we need a telescope. And then from there, we get our preliminary requirements, which tells us our aperture size and our contrast ratio, and what technologies that we'll need. So a deformable mirror, and what detectors we need, and how stable our telescope needs to be. And then from there, we can identify risks and mitigations. And a risk might be, how are we going to move this observatory around the country? And our mitigation is that we're pulling from the teams on Roman and Webb that have done this before, and they've got some ideas. And then from there, we get our schedule estimate, and then our cost estimate. And then we take all of this as our entire mission, and we feed this back to our science, and we ask the question, did we meet our goals? And when we can check the box on all of these, that's when we have a technical baseline and a programmatic baseline. And that's what we can take to our mission concept review. And in addition to our technical and programmatic baseline, we'll also have a lot of documents that we need, because we're NASA and we like to write our documents. But it's more than just writing a document. It's more than just a static bureaucratic process. It's a way to explore the trade space and have a plan that we execute to, because we need to deliver. So our plans and our requirements that we have are going to be captured here. We have our level 1s and our level 2s, which are just as important as everything else. I want to talk a little bit about our technology maturation that we need for MCR. So we have heard from the community, and we have our own scars of why we need to do this, so that we want to mitigate the risks. So we've captured this feedback from the large mission study in the Astro 2020. We've captured this in our technology plan. And we are maturing the technology to mitigate that risk. And how are we doing this? We're partnering with technology, with the industry. And we've been doing this for many years, and we've also need to continue this. So we are ready to award 7 proposals with industry, and I know they are ready to work as well. I want to talk a little bit about our schedule. So right now we are at our beautiful symposium. It's great. But then we have our broadly looking out to our mission concept review in 2029. So as we get there, we have of coming back. We have that cost and schedule baseline. We have all of our plans that we need before MCR that we're working on. Moving down a line, we have for system engineering, we have our EACs 4 and 5 that we're starting right now, but then converging towards that mission, that technical baseline. We're doing our instrument studies, where we start with our instrument studies that use EAC 4 and 5, but then our instrument studies flow into what is our EAC 6. On our science line, we have our, one thing I definitely want to point out is the HWO journal articles. So this is when we think it's going to be released, but our deadline for submissions is in November. So please make sure you get those in. We are also working towards our level 1s. We'd like to have our level 1s in parallel while we're doing our instrument studies so we can have that information feeding back. And the last one, of course, the technology, contingent on funding. We are ready to start that in October. I can't have a management talk without cost control. So this is the part that's not rocket science. There are a lot of ways that we can manage our costs, and we are going to use all of them. We're defining our requirements, and I know firsthand that there's a throttle between where your verification and how that feeds into your cost control, and then our interfaces and how our institutions work together. Active schedule management. So on the telescope for Roman, at one point we had 5 different assemblies, primary mirror, secondary mirror, etc., all within a week of the critical path. And we did that for more than a year. I didn't wear a suit that time. Risks and opportunities, I hit on this already, but it's just as important. Clear roles and responsibilities. As we as a project are transitioning from so many people volunteering and institutions volunteering their R&D to becoming a project, the roles and responsibilities become ever more important. Open communication. This is obvious but needs to be said. And technology maturation. This is one that I think we are doing a little bit different, and I really like what we're doing, where we're managing our technologies on when do we need it and what level of maturity do we need for our mission. And by prioritizing these, we can mitigate the right risks for our technologies. So in summary, we have a great team. This picture is from our CSET, and we've got our project office and a few from headquarters and even some interns in here. And I want to reflect back on our flagships that I started with, where Webb and Roman are at L2. HWO will also be at L2. And L2 is a million miles from Earth. And I like to think of a chain that is a million miles long. And everywhere along that chain, every day when you come into work, you're putting a link in that chain. And you're contributing to making sure our success. And whether you are a scientist or an engineer or an intern that just started putting your chains in the link, we are all part of that chain. And our industry partners and our international partners, we're all part of that chain. And I cannot wait to have everybody come and contribute their part to the chain. Thank you.
Okay, we have some time for questions. None. Everybody too tired? Fell asleep on the airplane ride.
Hi, I'm Thaís Storchi from the south of Brazil. Congratulations on the project. And so you have already the design of this enclosure. It's I didn't get if you are still going to modify this or if it is the final design.
First, I'll say it's not the final design.
Oh, okay.
But in the enclosure, are you speaking about the barrel around
the barrel? Yeah.
Yes.
I don't know the name.
Right. So it is one area that I am, if I write down my risks and mitigations, that's one area that I am concerned about is the barrel. And I know that we are working on what we saw was EAC 4 and 5. We need the barrel for really 3 reasons. It's for stray light, it's for thermal control, and an or micrometeoroid impacts. And so from those 3, that's really what is driving that design.
Okay. Thank you.
Thank you.
Another question right back there in the orange. I think you're closer.
Hi. So it's kind of a combination of the previous emerging technologies panel and this topic. So imagine in 2035, there's some new potentially game-changing technology for HWO. Are you guys thinking about that? How the schedule can adapt to that, and how to decide whether or not to adapt it to that?
So for me, I think the most important part is where servicing fits into that story. So I very much want to see the observatory serviceable for that very reason, where new technologies on instruments can be serviced for the 2nd or 3rd generation.
I'm going to ask a chair prerogative question to probe on that, because I was going to ask it during the panel, but I didn't.
Okay.
What about technologies that say new detectors that require cooling, right? So I can imagine some of these technologies might be easier or harder to include in a servicing mission. Putting a cryocooler on a serviceable module and then suddenly introducing that vibration to the telescope might be challenging.
Yes.
So like, in the landscape of some technologies that could be put, like, it's nice to say that we can just service things, right? And that we'll just punt it until we service it. But like, where are the breaking decision points on stuff like that? Because at some point, it feels to me like we probably cross a threshold and it's not a possibility anymore.
There would be multiple technologies to have to advance for that to work. So you would need an isolation system on your cryocooler. You would need to, there's a lot. And to think of, there's a lot of speculating, and I'd rather not.
One question from Steve, and then we'll have to move to our next panel.
Okay, great, thanks. And nice talk. In summary, Steve McCandless, Johns Hopkins. I'm just trying to understand where, when you get to MCR, are we still just going to be on like EAC 5, or are we going to have something more mature that we can then look at and I can start getting some effective areas out and know how many gradings I've got and that sort of thing? How locked down are we going to be at that point?
So we have our instrument studies that where you can get answers to that. We're going to feed all of that instrument studies plus the EACs 4 and 5 into what will be EAC 6, or our technical baseline. And once we have a technical baseline, that's the line in the sand where we can allow you to go do that. And that's what we take to MCR.
Okay, let's thank Scott again.
Thank you.
Okay, so that was our one talk of the session. And now we have a panel. So let me get this going. So I'm going to introduce Jim Oshman, who's the organizer and moderator for the panel, and this is an industry partnerships panel.
Thank you, and good to see everyone here.
on the fourth day. This has been an amazing week. I'm sure most of you are typically halfway through these things. It's already felt like at least a week, and so we're in week 2 here. I'll come back very briefly to what started on the first day and that Scott expanded on is we've now taken off on our next leg of our journey towards the Habitable Worlds Observatory on a plane. And for this session, for this segment, I'm your captain. But we're going to end up taking a little diversion because I think a lot of you expect we're going to continue to talk about technology here. There's been a good number of talks and things on that, so we decided to take a different aspect of how we reach the end game. So we're going to, due to some turbulence, go take a landing over in Collaboration City. And so our working theme that our panelists here wanted to talk about, and I totally agree, was how we work together to enable the Habitable Worlds Observatory. We, and it includes myself in my former role at Ball Aerospace, now almost 7 years ago, it seems like yesterday, we've had the companies represented here, along with many others, have a long history of, yes, both competing for projects, but also collaborating with projects. And on big missions, even if there isn't a direct contractual relationship, a long, long history of helping each other out because it's the right thing to do to have that mission succeed. So here the intent is to apply that same philosophy right at the beginning. Right at the beginning here, as you've heard from Scott and others on the process of these different EACs and the studies that led up to that, we don't know the final answer and result in here. And so, you know, industry can't go and just bid on something specific and go develop it there without working closely with our colleagues at NASA and the science community and to do a better job into supporting the vision that the scientists want to see here. So we long ago started working together, specifically talking about habitable worlds, building on the 4 companies here representing have a great working relationship from building something called the James Webb Space Telescope. It kind of worked out pretty well in the end there. So long ago, we started getting together to talk about how to approach that. So in this, yesterday in one of the technology breakout, if you were there, you heard a lot about the specific technology maturations that each of these companies and many others are working on here, and the excellent progress that they are making in each parts that they've proposed. You may have noticed that there wasn't a lot of overlap on the same issue with people competing with that. This is with the clear roadmap that NASA's developed, which these people have had a part of inputting to that. It enabled us to collectively get more done by working together in some form of coordination, whether it's formal collaboration, which has happened in some of the technical developments, or separate proposals, but they end up working together anyways, so we can move the technology in when money is limited further along. So it's all about what can these companies do, and I'll express the attitude, and I hope you'll expand upon this. It's not about competing for the work now, it's about how do we participate in enabling the large flagship type missions going forward. And think of that way right from the beginning. And I'll say we collectively, and I'm going to add myself to that, we really believe collectively with the community, we have the capacity to meet these challenges that are being discussed. Not an easy road, but it's doable. Another aspect of that that many of you may not be aware of, but these 4 companies, along with others, along with many in the audience here, do also collaborate in the messaging, not just to the public, but to our representatives that are key to obtaining the money to go forward there. So we're going to talk a little bit about that there on the industry part of advocacy, which is coordinated. It's specifically coordinated purposefully with other organizations to make sure everyone's aligned, having the right messages from a broad group of people to have the largest impact here. And with all of this, advancing such a thing, it is part of maintaining leadership that NASA has often taken the lead on these very, very large programs that also have room for effective international partnerships. But you have to enable those big programs that, that only NASA is capable to lead. So how can we help that from the very beginning there? And I'll say, you know, back on the technology maturation going forward, you should note that each of these companies have invested their own R&D dollars to extend the work that they're being paid for here. But through this, it helps maintain all of us to have leadership roles in enabling fantastic science that result in not only the science itself, but unpredictable, but we know it happens, economic and security benefits. There's a lot of cross-purpose type things and information that flows across many boundaries here where a lot of people are working together to enable these things. So with this, I'd like to turn to each panel member to do a brief introduction here. We'll go through a series of questions and hopefully get some audience participation towards the end of this. So with that, I'm just going to start from the left here. Here's Matt, if you could go ahead and introduce yourself and your statements.
Very good. My name is Matt East. I'm a mission architect at L3 Harris. 8 years ago, I made a choice to get closer to space exploration in my career and join L3 Harris. And little did I know that NASA was going to tee up an extreme collaboration opportunity for me, from HabEx to LUVOIR to the START and TAG initiatives to supporting the decadal survey in a small way, and now today to Habitable Worlds. I've been very lucky to be part of technology development teams with each of the organizations represented here next to me. And as part of that, developing not just the technology, but also the manufacturing readiness to make sure in all aspects we're ready to execute Habitable Worlds. Being part of this team is something that makes sure we don't miss anything. We have friends who can challenge us in productive ways to make sure that our individual technologies are going to work together when we bring them together to solve this problem.
Thank you. Jeanette.
Hi, I'm Jeanette Domber. I'm a Payload Systems Technical Fellow at BAE Systems, formerly known as Ball Aerospace, out in Colorado. So I've had the pleasure of working on 2 decadal missions so far. I worked on Hubble Servicing Mission 4 and got to participate in every instrument in one way or another. And I also got to work on the Wide Field Instrument for the Roman Space Telescope. And being here this week has just made me so excited again for the opportunity of Habitable Worlds. We're very proud of our history of participating in all of the major flagship astrophysics missions and as being a partner to NASA and with all of the community to create that wonderful science. And currently our claim to fame, besides our work on JWST, is that all 5 instruments currently aboard the Hubble Space Telescope were built out in Colorado by BAE. So, thanks.
Thank you.
Okay, I'm Alison Nort, and I'm the Director of Space Science and Instrumentation at Lockheed Martin. And I've been working in the field of space science for 26 years. I started my first day at Lockheed in 1999 working on the SIM mission. And then worked on an Astrophysics Explorer. And then when that one actually got canceled, that day I was asked to help on a proposal for an instrument for just 2 weeks to do some structural analysis on something called NIRCam. And then for the next 16 years full-time, I was on NIRCam. So I've done a lot of different things and saw every aspect from the proposal all the way through to launch on NIRCam. And then after we delivered and most of the work was down in John's shop on Webb, worked on WFIRST for a little while from some early studies, what became Roman, of course, and then all of the STDTs, most of the STDTs, and then have been doing technology development for HabWorlds for the last 5 years or so. So been working with all of these folks for a very long time, and very excited for HabWorlds and the technology development and the collaboration that we're doing together.
Yeah, and last is Charlie Atkinson. Wait a minute, what happened here?
Yes, well, we were talking earlier about AI. So this is AI hallucination. If you love the speech, I'm John Ehrenberg. If you hate it, my name is Charlie Atkinson. John's history extends back to his second day at what was TRW, now Northrop, when I was assigned to the AXAF, now Chandra mission, even as far back as that the collaboration amongst the companies, a number of which are here, was important to that mission's ultimate and continuing success. And I will note that it's on started the 27th year of its 5-year mission just a couple of days ago. I went on to work on Webb, all 4 of the Astro 2020 decadal surveys, and I do want to make a small point of history, is that even though we have collaborated as contractual partners, we went and took the extraordinary step of working together on the decadal studies. In fact, I wrote what we call the Edinburgh Manifesto with MacKenty when she was an engineer at Ball, and got signatories of the other companies to then go talk to the AD Paul Hertz to allow us to bid together as an industry team to extend the resources. And we've kept that cooperation both formal and informal, and I think it not only helped confirm to the decadal panel that Jim served on that a flagship was feasible, given all the tumult of the time of the late teens, to helping to work to bring HWO to reality. And that's what I certainly look forward to.
Great, thank you. I'm going to start out with some questions here. So thought I'd go to the political advocacy part that I alluded to earlier there. And I'm wondering if any of you or all of you would like to comment on what messages do you find resonate with our representatives in DC? How does it help maintain American leadership? And how can the audience get involved with advocacy? Anyone want to start it off? Alison.
I'd be happy to. Yeah, I've been spending a lot of time recently on trying to get advocacy for science, not just NASA funding or SMD funding, but science as a whole. And in talking to representatives who may not have thought that they were advocates, to try to make arguments for the future of the workforce and the national security implications of how civil space leads to superiority in technology and the makes America great, period. And the importance of continuing to fund research at universities, because every single one of us and every single person that holds a cell phone in their pocket benefited from research funding at universities. Every one of those cell phones was built by an engineer, and every engineer went to a university, and every university was there because the professors had federal funding of universities. And it is absolutely a travesty of what's happening right now in the universities, and that affects national security and space science, and we need to change it. So those are some of the arguments that are actually some of those are landing with some of the Congress. So
great.
Yeah, and to build on what Alison said, I think that workforce piece is really one of the parts that resonates. Like what we're trying to do now is, as we move from one great observatory to the next, is maintain that knowledge base, make sure we don't lose all of the things that we've talked about in terms of the lessons learned on Hubble, on JWST, on Roman, and roll those forward into habitable worlds. And so we built a great workforce, a lot of people who are knowledgeable, not just in the science community, but in the engineering community, in the finance community, and all of the parts that support how we can build these great observatories. And maintaining that workforce is really important to our representatives, and we need to do that without a big gap between these missions so that we don't lose those people. And what's happening right now, that's one of our major battles, is to make sure that we don't lose the knowledge that currently resides within NASA and the industrial base by giving them great opportunities like the technology development that we're doing and other opportunities to build on what we've learned and apply it to the next mission. And hopefully that next mission, well, we know that next mission is going to be habitable worlds.
Yeah, I might add, and that includes training the next generations coming up, because these are long missions. So the chances of any of us actually being in lead roles when this launches is not what drives us. It's the chance to enable this for the future here. But John, why don't we go to you?
Yeah, I think two quick things. Number one, if you want to advocate, pick up a pen or a keyboard or however you want to communicate, and exercise your right to talk to your elected officials about the importance of science. And in terms of advocacy as individual citizens, it's probably most effective to talk about science and science missions broadly, and then say my part is, and not have all the missions fighting each other as a tactic that won't work. And
Right. And we can add to that a lot of our professional societies offer opportunities to help structure how you can talk to your representatives if you're not sure how to get started. So the AAS, the American Astronomical Society, and SPIE both have things on their website that can help you get started. And then there's a website you can go to from Congress that will tell you who your congressperson is if you don't know, and how to contact them.
Matt, anything there?
I'll just emphasize Alison's point. The message around technology certainly resonates. We want to be leaders. The United States has a storied history of being the leaders in space technology in the world. We want to build on that. We want to compound on that and make it exponential. So this is the type of investment that gets us there.
Yeah, and adding our international partners to that helps us go even further than we could. But that leadership part, from my perspective, is still very important. Okay, let's move on here. Can each of you give a brief example of coordination or partnering resulting in notable technical process that's with NASA, your colleagues on the stage, or others? Matt, why don't we start with you?
I've been very happy to work with Janice, with the BAE team and with the Lockheed team on the Ultra and TechMass projects, respectively. On TechMass, we've been able to advance the state of mirror manufacturing to produce large UV quality mirrors at a rapid rate that's responsive to habitable worlds, and also develop some of the architecture trades to make sure that we're going down the right path with a solution for the large, stable, segmented telescope. On the BAE team with Ultra, we've gotten to advance the TRL of stable mirror assembly technologies, which is a lot of fun, showing in a thermal vacuum chamber in a representative environment, yes, we can actually achieve these picometer class sensitivities that are required to even go past what Roman can do. And of course, on Roman, we're collaborating with NASA Goddard, and we've been able to demonstrate, especially with Goddard's leadership, that these big flagships can be done on time and on schedule. And so far, we're on track to do so. So great experiences.
Let me mix it up and go to John at the far end here.
So I'll go back to when we were executing Webb as a classic example of maximum cooperation. There was a crisis with the cost and the schedule related to the Johnson test, the end-to-end system test. And a group of us, including our esteemed panel chair, were put in a small room, just a few of us, 7 of us, and took off our corporate badges and did the best thing for the program. We wound up with a simpler, smaller, more effective, and ultimately, highly productive test. And we did that by working together and working in a badgeless fashion. And also, if you go back and read the lessons learned from the Chandra experience, that was probably the top of the list that enabled that mission, was badgeless behavior. So I'll stop there.
Alison?
So we've worked with all of these colleagues, but I'm going to bring into another dimension of collaboration, and that's with the universities. And on our programs that you saw our logos up there earlier, we are working with several different universities, University of Florida, Illinois Institute of Technology, University of Arizona, on technologies that would advance habitable world, from picometer level metrology to coronagraph modeling. We're developing these with universities, with each other. On the integrated modeling front, Laura Coyle from BAE is doing a lot of integrated modeling. Our team on TechMast also doing integrated modeling, sharing results and seeing how they can collaborate, because there are different aspects of the giant ultra-stability problem that we need to work together.
Okay. I'm going to take a slight diversion on our landing here, or before we take off here, and just see if we have a couple of questions from the audience. But warning, I'm going to save a little time because I have one final question to ask. So if we can get the mics down, we have someone here in the middle and near the edge there.
Hi, Martin Barstow from University of Leicester. I'm really heartened by the degree of collaboration that we're seeing. But a question I'd like to ask you is slightly provocative. So I'm working in the UK. We want to build an instrument, potentially. We have to work with our industry and persuade our government that our industry benefits to get the money to support that. I would really like to see an opportunity to link together industrial companies in the UK with you guys so that we can maybe broaden this industry partnership internationally. And indeed, we do have a BAE Systems in the UK.
You have a Northrop too.
Yeah. So there must be some overlap. And we hosted the UK footprint of Northrop Grumman in Leicester. So I think I'd like to hear what you have to say about that, and hopefully it'll be equally encouraging.
Anyone want to?
Well, those international partnerships across industry do exist. For example, at BAE Systems, we were the spacecraft and payload integrator for the IXB, which is the, I'm gonna forget the actual acronym, but it was the X-ray polarimeter, a SMEX project, and we collaborated with the Italian Space Agency on that, and industry within Italy built key components of that. So that was on a smaller scale, but it does exist. So there are definitely opportunities, I think, for that international industrial collaboration.
John,
I was just going to say yes. I think it starts with a phone call, and so I think we're all thinking about how we might want to do that, so I'll just stop at yes.
And you can emphasize all of the benefits that industry in the UK will receive, because this is not just the global impact of the project itself, but it's also bringing in new talent. This is the type of project that attracts the best and brightest of early career folks to come into the field of science and technology. So that is absolutely a reason to do it.
Yeah, and that's a worldwide impact.
I'll just add on what Jeanette said about explorers are a great pathway to having done that. Like right now we're working on MUSE, which is a heliophysics explorer, and we have collaborations all across Europe and Australia, and there are a lot of international collaborations, and I think we need to bring that model into the flagships, which has been done obviously on web, but even within instruments, I think that there are contributions that go international.
Yeah, and I'll add briefly, it's been a pleasure to see, I've been a member of the START committee and chairing one of the working groups, but to see there's been representatives right from the beginning, from ESA, from the UK, from Japan and others there to participate. As a lot of you know, one of the early roadblocks is the ITAR considerations. So this is maybe, I'm not asking for an answer, but is there a way that we can address that and smooth that out process earlier, that we can allow some discussions there? But conceptually, I support us working together on this. I'm down to my last minute, so one last question for your answers. Are you ready for the next steps? Matt?
Yes.
Beautiful.
Yes.
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 With that, thank you. And by my counting, we have 16 seconds here.
We have
So
16 seconds left. Anybody want a last word? Or are you going to be the one
Yeah,
thing
we
that ends
delivered
early?
with margin.
Thank you, everyone.
How convenient that our next panel is on international partnerships. Okay, so time for our next panel. I'm going to introduce Megan Ansdell from NASA headquarters, who is the organizer and moderator for this panel on international partnerships.
Okay, good morning, everybody. It is my pleasure to be moderating this panel on international partnerships. This is a topic that's very near and dear to my heart. And we have a fantastic lineup today of leaders across space agencies, a few space agencies. We'll start with Sean Domingo-Goldman from NASA. He's the acting astrophysics division director. We then have Caroline Harper, who is the head of space science at the UK Space Agency. Keigo Enya, who is at the Japanese Space Agency, JAXA, and he is the HWO study task force lead there. And then we have Paul McNamara, who is at the European Space Agency, or ESA, and he is the astronomy and astrophysics coordinator. And then finally, we have Jean Dupuis at the Canadian Space Agency, and he is a space astronomy senior mission scientist. So I would like to start by doing a bit of a round robin with the panelists and just share with us how your agency approaches international partnerships, in particular in the context of HWO. And I'll start with Sean.
So first of all, thanks for joining us here today. I think the HWO is a great opportunity for our international partnerships. We've gotten a lot of interest in that internationally. And I think for the agency, it's a great opportunity for us to demonstrate the value of international partnerships. This is an administration in the United States that's always looking for a good deal. Our international partnerships are always a good deal to the United States of America, to the American taxpayer. And we think that this is just one of many examples of that. And so we're really looking forward to the opportunity to demonstrate that to other members of the administration because we do think there's value in all our partnerships and collaborations. We either pay a small amount of money on internationally led missions, and then we get access to world-class data for the things that you all lead. And then when we lead a mission like we're planning to do with the Habitable Worlds Observatory, you all bring your own funding, and as we heard on the last panel, industry capabilities to the table that complement our own. And either way, it's a good value to us, which we really appreciate.
So in the UK, I'll start by saying that we have a huge amount of interest in the science capabilities of what HWO will be across the whole gamut of the subjects that we've been hearing about this week, and in particular on exoplanet science and inspiration and instrumentation, of course. We have a long history of pulling together international teams to deliver amazing science missions for ESA and NASA. And we have a particularly positive experience to report on JWST, where many of you will know that the UK led the European consortium that designed and built the mid-infrared instrument. Excuse me. And that was a really good experience for us. We worked in partnership with ESA, we worked in partnership with NASA and with US labs, and that's something we want to do again. So that's where we're sitting at the moment. We're keen to lead an instrument level contribution, and we're looking into ideas for that now. We've also got interest in the UK at subsystem level on HWO, contributing to other instruments led by other countries. We just want in, really, into this human history defining mission. I mean, who wouldn't want to be part of it?
Okay. First of all, my name is Keigo Enya from JAXA. First of all, can you hear me?
Yeah.
First of all, thank you very much for your organizer and moderator and everyone in this conference. Recently in JAXA for HWO, participation study team, task force team is formed in JAXA in last in last December. I think this is JAXA thinking international part of the partnership is very important and essential. And I think this task force is means JAXA is very seriously and highly motivated to participation to HWO. This is evidence of it. And for hardware contribution, JAXA has big interest in infrared coronagraph hardware, especially coronagraph hardware, especially infrared, and also UV hardware. Okay.
Thank you. As Paul McNamara from the European Space Agency. I think in terms of collaboration, the first thing to say is that ESA itself is an international space agency as opposed to a national. We have 23 member states, one being, say, UKSA. So all of the missions which we do are, by definition, a collaboration of these 23 different countries. In terms of our international partners, this is our 50th anniversary this year, and we've launched 41 science satellites over the 50 years. I think roughly 25 of those were with international partners, and we have 11 missions in development at the moment, and 9 of those are with international partners. So by definition, we like to collaborate. We see the benefit that if you want to get the best, then you look beyond your borders to get the best you can for our missions. And for HWO, we'd like to follow what we've done for some of the other great observatories with, say, Hubble and JWST, where we're a major contributor. Also, we contribute to Redmond to a lesser extent, and we'd love to be part of HWO.
Hello, so I'm Jean Dupuis from the Canadian Space Agency. Thank you for inviting us to be on the panel. So CSA is really at the core of our principle to do a project in partnership nationally, internationally. As you may know, we are a proud partner in the GWST mission, to which we contributed the fine guidance sensor and the nearest instrument. We're so happy about the results, about this collaboration. We learned a lot from it, and I think we're proud to be a contributor. We have also history of being interested by UV astronomy. We're part of the FUSE mission, a NASA mission, to which we contributed a guider, a fine array sensor that was used for guiding. We contributed UV detectors for the AstroSat, for the UV IT instrument aboard AstroSat, ISRO mission. Also, for the Canadian community, UV astronomy is very important. There's like a community goal to have a Canadian-led mission called CASTOR eventually. A lot of the technology we've been already developing for CASTOR is relevant to HW detectors. There's work doing by the National Research Council of Canada on the prototype of UV MUS. So we're very excited about HWO. This week we're about to publish a request for information to the Canadian space sector, where we're seeking input on more defined ideas on potential contribution.
Great, thank you, everybody. So we can move into more of a discussion amongst the panelists, and what we've heard a lot this week in terms of a theme is what we learned from JWST and Roman and what we can carry over to HWO. So I'd love to hear from the panelists what they think, lessons learned that they've had from previous experiences. And let's start with Caroline, since you brought up the UK-led consortium for JWST, Mary.
Sure, okay. So I'm going to start to answer this question by saying that as far as HWO goes, there are 2 reasons why, for me personally, it's really exciting. One is the transformative science that it's going to do, for sure. We've talked a lot about that. For me, the other thing is the transformative relationships that we're going to build and nurture through coming together to do this thing. And I think that's a lesson that we learned from JWST. It's not possible really to overemphasize the importance and the intellectual benefits of having that diverse international team with different perspectives, different experience, different engineering experience, different problem-solving approaches, all essential if you're going to come together to do something so challenging that it's never even been tried before. And that's really important. And then I think the other thing is probably, if I talk to the people that I know in the UK who worked on JWST, they would say that there were really good management and governance structures put in place. And I think by experienced institutes and a talented team of people who could evolve as the project evolves. So none of that's rocket science, to quote what Scott said earlier, but it's important. It needs to be said. It's the right people working together at the right time, enabled by the right structures, and that will be the difference between success and failure. And I think I'd also say, if I may, that from our experience on MIRI was that the project benefited enormously from being able to work with ESA, as well as having an independent identity as a nationally funded European consortium. I think that worked very well. Paul, I don't know if you would agree with me. I hope you do. Perhaps bring you in there.
No, I fully agree. I think, so for people who don't know, within GWST, ESA provided the near-spec instrument and then also worked with the collaboration to do MIRI. And I think that was a very strong link, both for near-spec and MIRI. It goes both directions. One thing I'd like to add in there is, particularly for JWST, when you're working together, you really are getting the best of the best. But there's also a trust goes between both sides. And I think it's very clear to say that NASA trusted ESA to launch, which was the biggest mission you had. And it was launched on Ariane 5 under ESA contribution. So from...
And it was well placed. Thank you for the spectacular launch.
But we, as I said before, we have all of our missions in collaboration, and we have many missions where we have collaborated to a NASA mission, and we also have missions where NASA has collaborated to ESA, also with JAXA and Canada. So by doing this collaboration, you really are picking the best of the best. You don't have to be so insular, you don't have to look within your bounds, you can look outside, and then you always want to make sure when you get to the launch pad, you have the best instruments sitting there. I think you do that through collaboration.
I think for me, one of the lessons is making sure that we have the flexibility to bring whatever partnerships make sense technically to the table. And this is one thing that we'll, not just us at NASA, but in the United States, but throughout the community need to keep in mind, because a lot of our conversations, space agency to space agency, or with consortiums thereof, are focused on those instrument level type contributions. We also want to make sure we're keeping the door open to those component level contributions, which you heard about. We aren't necessarily going to be telling all of you that if you're leading an instrument, where those components might exist. We're going to trust the community to identify those relationships where they make sense, whether it's an internationally led instrument with components from other space agencies, or a domestic led instrument with components from other space agencies or other nations. We're going to trust the community to figure that out, which means it's also incumbent not just upon myself and my colleagues at the table or online, but upon yourselves as community members to also identify those opportunities where they exist.
Okay, so following on from that, there's a variety of ways to contribute to a mission.
To set you up.
It was well done, though. There's a variety of ways to contribute to a mission, and not all of those ways end up going into space. So ground-based assets are something that is also a contribution. So, Keigo, I wanted to ask if you could share what JAXA is doing with Roman in terms of ground-based facilities.
Okay. Yes, in this topic, there are two ground-based telescopes relating Japan. One is Subaru telescope in Hawaii Island. And Subaru telescope will provide 100 night observation time for Roman after Roman launch during Roman operation for the synergetic science observation. The second telescope is Prime telescope. This is 1.8 meter diameter telescope developed in South Africa. And in this purpose of this, this Prime telescope will be used for the preparation for Roman observation before Roman launch, and also will be used after Roman's launch, simultaneous observation for the special science objective, parallax microlensing.
Paul, I know that ESA also contributed ground station, so would love to hear your thoughts on what that contributed.
Sure. So there was talk earlier about going to the Lagrange points. We also have several satellites out at Lagrange points and also the planetary satellites. And they require the large ground stations, so for our case, 35-meter antenna to do the communication. And we have them located in Spain, Argentina, and Australia. The fact is they're not used all the time, and when you have any mission which requires the Deep Space Network, then we're very happy to use our network, as NASA is also using DSN to help with our missions. It's another way where we can collaborate. And getting that data to the ground, we're all scientists, we all want to get the data, there's no point in having it on board. So then we can actually use our, between the two, having a K-band telemetry really ups the telemetry rates.
Okay, the final question that I have for the panel was stolen by Martin Barstow in the previous panel. Thank you, Martin. But perhaps we can continue the conversation that the last panel on industry partnerships ended on. So can you, the panel, discuss how you engage industry in your international partnerships and how those sort of are interweaved? Maybe we can start with Jean.
Yes. Yeah, so CSA works very closely with the industry. All our projects are being executed by Canadian companies, and we try to involve them as soon as possible in the, I will say, in the project definition and interfacing with our international partners. So we think it's very important to proceed this way so that we have everybody on board as soon as possible. We try also to be very inclusive of the science team, mainly from academia, so that we have good communication among everybody.
Maybe I could say something there. So there's been lots of talk this week about picometers. We had a mission launched a few years back called LISA Pathfinder, and we were measuring femtometers. At the start of that mission, when we first started talking to industry, scientists think picometers are okay. The phrase was coined called picophobia, and picophobia was a fear of large negative exponents. And when you talk to industry, immediately it's impossible. It can't be done, forget it. When you start working with them and you start explaining what does it really mean, what does it mean at the component level, the integration level, suddenly it's doable. And within a few short months, our industry had then taken over. And they led that. And LISA Pathfinder was a collaboration between ESA and NASA. In order to achieve picometers, you cannot be working independently. You have to work close together. And so we had very strong links between the two teams on both sides of the Atlantic to allow us to achieve, which they said, in the end, with requirements of picometers, we measure femtometers. So it is doable.
Go ahead, Carol. This is one of the things that I think in some ways helps our conversations, because anytime you're engaged in a conversation or a partnership, it's really important to have an understanding where the person or the people on the other side of the table are coming from. And so if our international partners are coming to us and saying that one of their interests is to make sure that they're developing their industrial base in their nation, I get that, because that's a big part of what we are doing at NASA as well. We are incentivizing the creation of technologies that, as we just heard from that wonderful last panel, our industry members are advancing, and then they're turning around and using that for other purposes. And that makes our nation stronger, and when they want to do that on their side of the partnership, I understand that immediately, and it's one of the things that can help facilitate the partnership, is having that. Even though it's the same kind of goal on both sides of the relationship, and we're on the same page when we're having those conversations.
I was just going to say, LISA Pathfinder, I remember that well. What a great mission. I'll stick with the MIRI example because it's particularly relevant to what we're talking about here today. When we set up the consortium that the UK led, the European consortium, to design and build MIRI, we needed to include industry in the mix very definitely. And we took our time working out how that was going to look, and I think that was a smart move, and we ended up with a good solution. It was a little bit contentious at the time. It was a little bit unusual in the UK to do what we did, but we pulled in Astrium in the UK, now Airbus UK, and they took on the project management of the whole European consortium. And then the PI, Gillian Wright, in Edinburgh, was working more closely on the interfaces with all of the consortium members for sure, but also NASA and the US labs and Canada. So there was a real good division of labour there. Excuse me, I'm sorry. And I think that was one of the reasons that MIRI was such a success. If you talk to people who are in Airbus now, who are involved back then, they still talk fondly about the MIRI model and how great that is. And they're very, very proud of the fact that the MIRI was the first instrument to be delivered, and they still talk about that now. So there's a lot of pride there and a lot of passion, and it was really good to have that combination of academia and industry working together so seamlessly. And I have to say that the knowledge transfer and the academic industry partnerships that we developed as a result of that, we're still reaping the benefits of that today. So it's a very strong story.
Okay, so I think we can take a few questions from the audience, and then I'll come back and ask the panelists to all say some final words.
Okay, we have a question online from Michael Best, who asks, for emerging international contributors, including those outside traditional institutional pathways, what's the clearest route to having a meaningful impact on missions like HWO? And is there a risk that unconventional but high potential innovations might be overlooked because their teams aren't already in the system?
I think the first thing I'd like to say is it's not too late. We are still forming our collaborations. That's a lot of what we were talking about this week, but that is and will be an ongoing conversation for some time. Frankly, what we want to make sure we're doing is identifying those potential collaborations now, so that they can be studied in parallel with and at the same fidelity over time as what we've been hearing from our project team all week and what we'll hear from Scott later today. I think if you've got an idea, make sure that you're reaching out to us through your space agency or through your international connections to the United States and to NASA. If you're not at the level of having an instrument level contribution, the best way to get involved is to be involved with this community so that you can connect to instrument leads both in the United States and abroad. And I'd add one other thing, which is even if you're just an individual scientist or subject matter expert, you could be engaged in this endeavor just by being part of this community and the community-wide activities that we're spinning up all the time. I don't know if any of you want to add to that.
Well, I'll just come in quickly and say that one of the things that's been really encouraging and impressed me this week is the openness and the open-mindedness of the dialogue with NASA. I think just everything is on the table at the moment, and I think the message we've received is we don't want to stop those creative juices from flowing, so keep the ideas coming. Everything's open at the moment. Let's talk. So yes, just to echo what you're saying.
I'll add one more thing. Just in terms of how these things happen. So if you're at the stage where you don't know how to get started talking to peers and colleagues across national boundaries. Because usually the ideas that we end up supporting formally space agency to space agency have already been identified as something as a technical value add to both agencies by the technical experts who we have in place to trust. So talk to your peers first, and then those ideas can bubble up to our level.
We have other questions from the audience in the room. There's one right there.
Caroline Einer from the Paris Observatory. In previous committees like STDT, START, and TAG, etc., we had international representatives. Right now, the CSIT is purely US, so I was wondering how you're planning to include international partners in the CSIT. Of course, an ESA representative, I imagine, but also from France, UK, Japan, Canada, etc.
Great question, and I'll say one of the things that's been great about this week and this conference is I was able to have conversations with everyone else at this table and a few other people in the audience about that very topic. What we're planning to do is add CSIT members, and I'm going to be honest about the two pressures that we're under as we do that. We want to add enough CSIT members so that we can have that parallel conversation of making sure that instrument level contributions are advancing at the same rate as the things we're studying in the United States. We need enough members to represent the total set of potential contributions at that level. And that would mean more people. At the same time, we've asked the CSIT leads, the CSIT co-chairs who are doing a great job to lead that effort, and we don't want to give them too big of a group to manage. And so we're going to take the next probably couple months to figure out how we're going to balance those two pressures, properly represent not just the family of nations that want to be a part of this, but the superset of potential technical contributions they'd like us to consider against having literally too many people at the table. We also would plan to have some venue like this, maybe not this large, but someplace for those smaller level contributions to be facilitated at the component level between different instrument concepts. TBD on the details, but they'll be coming.
All right, we have 1 minute left, so how about we go through the panelists and say any last words for the audience, and maybe we can start at the end. Which one?
Yeah, so I think this meeting was great, and so I guess my message is that Canada is open for collaboration, discussion. I encourage scientists to get in touch with Canadian scientists, maybe industry to speak to each other. So we're there to, we're open to, I guess, collaboration.
I think the only thing I would say is, to go back to our former president, he said that we don't do things which are easy, we do things which are hard. I think what we've learned within 50 years of ESA is when we collaborate, the harder becomes much easier. So I think we really have to do the collaborations.
International collaboration is essential and important for JAXA and for HWO. JAXA is highly motivated and seriously actually moving to participation to HWO, no doubt. Thank you.
Well, I'll go back to what I said at the beginning, which is this is going to be a great mission, not just because of the science, but also because of the potential for international cooperation and collaboration. That's bread and butter to us. We're looking forward to it immensely. We definitely want in.
Well, I want to thank you all for being here and for the conversations we've had this week, because I think we've really advanced our understanding of how we can work together as a US-led international community to change how we view ourselves in the cosmos. And I look forward to continuing those conversations over the coming years. Yeah, I think I'll leave it at that.
And I will wrap things up by sharing a quote that was brought up when we were prepping for this panel, which I think really nicely epitomizes the importance of international collaboration. And it is, if you want to go fast, go alone. If you want to go far, go together. So with that, let's thank the panel.
Okay, so we're at the end of the last plenary session. We are going to end with a audience participation, shared presentation from John O'Mara and Evgenia Shkolnik, and I asked them for bios, and I got some pretty great ones, so you're going to get to hear them. So John O'Mara is the Chief Scientist and Deputy Director of the WM Keck Observatory. He served as the Cosmic Origins co-lead, along with Jane Rigby, for the LUVOIR Large Mission Concept Study, and as the co-chair with Courtney Dressing of the Science, Technology, and Architecture Review Team for HWO. And my favorite part of his bio, John frequently travels a couple of blocks from here to advocate for ground and space-based astronomy on Capitol Hill. And in the 12 minutes per year he has to do science, he studies the circumgalactic medium. Okay. And then Evgenia Shkolnik is a professor at Arizona State University. She is the PI of the UV small satellite Sparks that will be launching later this year, and she's the deputy PI of a mission concept that I'm actually PIing, so I'm a little biased here, called EVE, the Early Evolution Explorer. She was the co-chair of HWO's Solar Systems in Context Working Group and is now the co-chair with Dave Charbonneau of the HWO Community Science and Instrument Team, and they are going to inspire us all to take the next step towards HWO.
Well, wow is what I have to say about this week. I hope you all feel the energy in the room, and it's been an incredible week. So John and I and my co-chair, Dave Charbonneau, were all asked to reflect on this week and provide some vision to move forward. Unfortunately, Dave could not be here today, So Dave, if you're watching online, a shout out to you. John and I will hold the fort down. But of course, we can't really reflect on the week without thanking the people who made it possible that we could all come together. So we're going to do that first. Here is the list of your local organizing committee, also known as HWO 25 flight crew. Now, we don't have time to go through all their contributions, but that will be happening today at 1 o'clock on the 8th floor. So please bring your lunch, if you like, to the 8th floor, and you can hear the acknowledgments dedicated to those folks. But I think we should give our LOC a big round of applause. Woo! Absolutely. We also have a very exciting science organizing committee, which I would actually rename as the Science and Technology Organizing Committee, because as you saw this week, we had a beautiful blend of science and technology, and I really appreciated that this team did that they were intertwined. It wasn't like we had science on day 1 and technology on day 2. It was beautifully mixed together. So I want to give a round of applause to these folks. Okay, and one more. We should put down our laptops and stand up and give Janice Lee a big thank you. Really, her commitment to HWO and this community has been very moving. Okay, I'm not going to get misty-eyed. On day 1, I already got misty-eyed with Jason's talk, and this is not the time for it. Okay, so back to reflecting on this week. So what did we see this week? We saw each other, which was so beautiful and amazing. It was a global team, an international group, as you saw up here, of over 400 people from academia, from industry, from government. We had multiple generations. We had veterans from HST, JWST, Roman, who are here to bring their experience to Habitable Observatory. And we also have the rising stars, right? Our early career scientists who are going to be there with us to make sure that the Habitable Worlds Observatory comes to fruition and to do the paradigm-shifting science that it is going to do. So thank you all for coming and bringing your A game this week. What did we hear? Well, we heard a lot, and I cannot summarize all the incredible science and technology we heard. We heard 47 plenary talks, 36 parallel talks yesterday. We still have 39 parallel talks this afternoon, right after lunch. Consider it like dessert. There's always room for dessert. Please come this afternoon to the parallel talks. We had 10 wonderful panels, 110 in-person posters, 67 online posters. That's 309 presentations. And by my skimming of all of them, it was a beautiful balance of about 50-50 between science and technology. So thank you to the STOC for making sure that happened. And a reflection that I had then being here all week, and I have to say, even though it's been 4 very intense days, I'm very sad it's coming to a close today, is that this really feels to me as a community-driven flagship mission, which might actually be the first time that this has been done at this level, with such intensity, such commitment, and we need to keep that kind of community engagement all the way through. So, what did we feel? Well, I can only speak for myself. I feel a lot of optimism and excitement, but I expect I am not alone. I'll tell you that when I walked in on Monday morning, put on my badge for the first time, before I even got to the coffee lineup, I ran into my co-chair, Dave Charbonneau, and I said, like what anyone says in the morning, Dave, how you doing? At which point he pauses, looks across the room, you know, from his height, he has a better viewing angle, and he says this to me. This is the dream. And then I kept my ears open. I was like, wow, what an interesting thing to say, and it's so beautiful. Right there on Monday morning, no one said a word yet. No one stood up on this stage yet, I started listening to what people were saying to me throughout the week, and I recorded some of this. A senior astronomer said to me, "I'm overwhelmed and excited." When are we all so overwhelmed as we have been this week? A graduate student said, "I'm so excited to see so many other young people here." Also amazing. A postdoc said this to me in the lunch line yesterday. "In these tough times, HWO gives me hope." A very seasoned senior astronomer, someone who has seen many a flagship, said to me, "I've never felt more optimistic for a flagship." And then, of course, we have very optimistic people, right? A very extremely optimistic astronomer said, "Let's do a 40-meter HWO." And thankfully, we have practical and cautious senior astronomers like Bruce McIntosh, who created this for the Slack channel, for those of you who aren't watching. And he reminds us that Astro 2020 said, about 6 meters. Of course, we're going to push to 8. But it's good. We have everyone on board. So all this enthusiasm, all this excitement really shone this week through the SCDDs, the science case development documents that the community pulled together. We heard lots about them. They really made up many of the talks and the posters and also of the conference proceedings that you will soon receive. And so they were broad in science and yet amazingly integrated, right? So we heard about planetary systems that included the solar system, exoplanetary systems. We had the search for life, of course, because that's one of our, for sure, big driving science cases. We heard about stellar and galactic ecosystems, and of course, and even the cosmic structure in black holes, as I think, Vivian, you pointed out yesterday, how this is really digging deep into our origin story. And so one thing that I really felt and saw this week was an effort to integrate all the science into a unified vision for Habitable Worlds Observatory. And I think that is beautiful, and I think we should keep going down that path. And I would like to say a huge thank you to the people who put those 70-plus SCDDs together from the CSIT, the Community Science and Instrument Team, and I can only assume the project office feels the same way, so I put that in there too. So what's next? So I wanted to, as a representative of the CSIT, I just wanted to say what we're going to be doing next with these SCDDs. Right now, we're reviewing all of them, and we're identifying the high-impact design driving science cases. And the important point here is that even though we received so many compelling science cases, some are harder to do than others technologically. And so even though we're going to have to eventually whittle down to a handful of driving science cases for the instruments that we want to build, there's many more compelling science cases that have already been written up, more that will come through, that will get done if we push the technology to the driving ones. The CSIT as your connection to the project office. We report directly to JADA. We want to continue hearing your science and tech ideas, right? Nothing is yet set in stone, right? You heard this also from Sean just now, that we want to hear more from you. So if you have ideas, please reach out to us. We are also ambassadors, so we're not just taking information, but we're also presenting information to anyone who wants to hear about Habitable Worlds Observatory and what the project office in the CSIT is working on. As we heard, there are currently 15 US-based CSIT members, and we will be including the international partners as well in this team as soon as they are selected. So please invite us to your institutions, to your governments. We are here to come and share. And then what we're going to start, then we'll also be doing is shaping the level 1 science requirements and help with the design reference missions in order to iterate the designs, right, to get from EAC 4 and 5 and ultimately to 6 ahead of MCR. And we are also tasked with evaluating instrument concepts and support maturation plans. So we have a lot to do between now and MCR, but we are also here for the community and to get all your input. And so all of this input, all of these things, the science, the technology, the requirements, are all going to feed into a beautiful instrument suite that we heard this week. One thing that we know for sure that Habitable is going to do is go from the far UV to the near IR. Now, where exactly that cutoff is TBD. That is going to be driven by the science. We don't know how blue it's going to go or how red it's going to go exactly. But we know, we have an idea of the kinds of instruments we want. The community has already told us this. We're excited about a UV IFU. We're excited about the multi-object spectrograph. Of course, the coronagraph that is going to be hard. We know that. But we also know how to do it, how to get from here to there so that we can observe our exo-Earths, detect habitability, and do all sorts of other science, including protoplanetary disks and other imaging that I heard this morning on one of the panels. And of course, we'll also have a high-resolution imager, which we are looking forward to pointing at solar system objects and distant galaxies. And it's going to be an exciting instrument. And how fortunate are we to even be able to contemplate yet another fifth instrument that will hopefully be contributed from our international partners and has yet to be determined. So that is where I'm going to leave off and pass it off to my co-speaker here, John, where he's going to dive a little bit deeper into the science and into the vision forward.
Thank you very much. So, once upon a time, I was a liberal arts professor, and if you're a liberal arts professor, you have two important things to convey, right? Interdisciplinarity matters, and context is critical. And so I really love Evgenia's framing here of the fact that the science is becoming ever more and more intertwined as we start to contemplate this observatory. And so I just want to walk through that briefly and try to convince you all that, yeah, okay, exoplanets have Riz and they're really hot and all that stuff, but that the context of those exoplanetary systems, the context of those stars, those galaxies, the whole universe, that's what matters. That's why we're building this thing, right? So in our local neighborhood, we have planets that we should observe to inform what we think about exoplanets, right? But those planets in our solar system gain context from these new solar systems that we're finding out throughout the universe. And we still really need to understand how they got there, how they were born, how they evolve, and when they die, how they influence their environments. And if we do this, if we actually do this, biology reaches out into the universe and discovers other biology, we are going to need every aspect of astronomical sciences, in fact, every aspect of science writ large, to both confirm what it is and to have it make any damn sense, right? Because if there's 0 of these, we've learned something important about the universe. If there's hundreds of these, we've learned something important about the universe, and we have a lot more work to do, right? To understand that context of either of those solutions. And it's really fascinating to think about, not only are we going to go out and search for life, but we're going to search for life in different times out there. And Giada kicked off this conference by asking you all to take a breath. So please take in that deep breath again. But please don't do it on Archean Earth, because you're going to have a bad day. I like to think about that oxygen that Giada motivated from biology in a cosmological context, right? We learned in the first half of our astronomical journeying in the 20th century that oxygen came from the local environments of the galaxy. Stars exploded, informed the interstellar medium. We got the oxygen here on Earth, and then biology happened. But in the first half of the 21st century, we learned that the oxygen, half of it that you're breathing right now in that breath that you took, came from outside. And then you have to realize that if you're wanting to discuss that cosmic history of the oxygen, you have to zoom out. You have to keep zooming out, or you won't get the story right. So if you zoom out at this really sad Hubble resolution compared to HWO, right, you see this beautiful plethora of galaxies of every shape, size, and color. And when I look at this, I actually think of Carl Sagan. saying, that the Earth is a mote of dust in a sunbeam. Well, galaxies are motes of dust in the dark rivers of the universe. And it's that context, that intertwinedness of all this science that makes this mission so exciting, right? The most effective way to do it is to do it. And we've started doing it, right? I look out in this room, and I am equally filled with hope about our ability to continue to build that. And it won't look like that. It'll be bigger. Sorry. Right? For me, this has been a very personal story, and I think a lot of people in this room have experienced something like this in this fashion. Right? Way back in the day, in 2016, in earlier, simpler times, I was asked to join the LUVOIR study, and the LUVOIR study, one of these large mission concept studies, and that's where I was first introduced to what John Arabig talked about, the badgeless team, the true team effort across science, engineering, programmatics, international, and all of those things. And this was how it started, right? Here's where we're at now, right? The decadal survey with Astro 2020 recommending, right, a large tilde-6 meter aperture, right? But I love the framing around it, right? The scientific goals of this mission, when achieved, have the potential to profoundly change the way that human beings view our place in the universe. I love that. And at that moment, once we started the start and all of the things that flowed from there, it was very much like the ending of one of my favorite movies, which was Finding Nemo. They're all working together as a badgeless team in the tank to get out of the dentist office and return to the harbor. And they did it. And this is the last line of the movie. We're there now. Now what? And curiously, Janice pointed out to me when I was looking at this yesterday that at this moment, all of them are individually back in bags. They're siloed again. The second you pop those bags, they go into the ocean, their community. We've heard over the week and all of the work that's preceded it about things like this, technology roadmaps. With all due respect to the extremely hard work our friends in technology are doing, I think this is the easy part. I think this is the easy part because if I've learned one thing, sustaining communities is hard. This has a roadmap. This has a plan. It is very hard to articulate and plan explicitly how to maintain a community. Right? Evgenia phrased it as this is a community-driven observatory. It must be community-driven for decades for us to get to the launch pad and realize the vision. Right? This is the Hokulea. It is a voyaging canoe that was constructed in the 1970s with the bold idea of redoing what had been done in the past. Hokulea's initial mission was to go from Hawaii to Tahiti. When Hokulea was conceived, when this mission was conceived in 1975, Hokulea traveled shortly after that, there was not a single living person in Hawaii who knew how to do this. They had to learn from Polynesian voyagers in Micronesia who shared that precious knowledge with them. They had kept that knowledge close to the chest for centuries. But in realizing that that knowledge might die with them, they shared it and the voyage began. This is community. This is resolve. Hokulea went to Tahiti after fits and starts, a couple of tragedies, but then Hokulea kept voyaging and eventually, with no motors, no navigational equipment, circumnavigated the Earth. We're at that point. We're staring out at the ocean, waiting for the stars to tell us where to go. Hokulea did it because it held community. It captured more community as it journeyed. Every time Hokulea came into a port anywhere in the world on its journey, thousands would show up to celebrate the moment. That grows the community. We have to keep growing that community. And what I love is seeing community writ large, right? this captures approximately 10% of what's going on right now, if not 1% of what's going to be going on going future. When I look at this community, all I can say is thank you, right? Thank you to the people who worked tirelessly to get us to the point of Astro 2020, and then say, now what? Thank you to the start and tag that preceded the CSIT and all of this work. Thank you to our industry partners who have been badgeless, working with us for decades to get us to this point. Thank you to our international partners. Thank you to the future users of the observatory in the front row there, right? Thank you to the early career folks who, in walking around saying they have hope, have given me so much more hope than they have. And right now, at this time in history, I personally want to thank NASA. Because at this time, they've shown immense professionalism and commitment to mission in a very difficult environment. So I want you to join me in thanking them. I'll close with my favorite proverb in Olelo, Hawaii, the language of Hawaii. Ho'okahi ka'ila o like'ana. Wield the paddles together. Let's get to work.
Okay, we have you guys hearing me okay? Yeah. We have 3 minutes left together in this morning session before lunch and then dessert. And so we're going to ask you a question to get you guys thinking as you leave this meeting, get on the planes tomorrow or tonight. What are you most looking forward to as we build HWO together? You can raise your hand. We have the mics. You can talk it over lunch with your buddies. But if you could share your thoughts right now, that would be wonderful. One right there. Thank you.
Hi, Kyle Cook from University of Louisville. You mentioned what are we looking forward to as we build this, so this isn't a science answer, sorry for everybody. But I'm looking forward to the things like this as a graduate student, being able to be present here, to make the connections, to meet the people, to have this project to carry through my career, and at some point hopefully see this launch and say, I was a part of that. And to get to that point, and I see HWO as like a career-defining moment for me. So just being here and meeting everybody and being a part of it's been, I think, the thing I look most forward to.
Amazing. Great answer. Any other hands up there? Oh, there's a few here.
There's lots of hands.
Thank you. I'll echo what Kyle was saying about being able to be a part of this. Growing up, I would look up to things like Hubble, later on JWST, and now we know there's hope for HWO to come online. So both being part of the process and knowing that these types of missions are going to continue and to be part of carrying that legacy forward is really what I'm looking forward to.
Beautiful.
Hi, Kyle. Another Kyle here. Kyle Dalrymple from Johns Hopkins University. I'm looking forward to hearing the gasp when people see things that they once thought were impossible. And I was talking to Brianne about this, and the feeling that you get in the audience when other people around you who've been working towards a goal for so long are astounded by the results that they see is truly powerful as an audience member and hopefully a contributor to that one day.
Amazing.
I'm looking forward to lying down in the old age home, and I turn on the TV,
and I see this room full of all the young people in this room, and they're showing images from each of the instruments and spectra of Earths. That's what I'm looking forward to.
All right. For you, Lee, for you. Well done.
I'm looking forward to paying it forward.
Yeah.
Oh, there you are. Right here, there's a hand. A hand down here.
As an intern right now, entering the workforce, I see the rest of the world is focusing on private interests and just seeing the micro level and focusing on what's here right now. I'm excited for what's greater and grander than us, right? And I think the community and the drive and the purpose beyond us. And on the engineering side, to be able to enable what science wants is what makes me happy.
I feel like we should end with Giada.
I'm looking forward to doing this together, right? We've never had a NASA flagship that has involved the community at this level this early on in the process. This is the first time we've done this, right? We have had over 1,000 of you express interest in this project, and I hope that grows, and I hope that snowballs. And John, you made me cry when you were standing up there talking, because we need all of you to do this together with us. You know, it's not just NASA who builds these flagships. It's our industry partners, it's our private partners, it's our international partners, it's academia, it's the community. We are all going to do this together. We are all evolving how we do flagships together. So thank you to you all, because I am so looking forward to this journey, right? It's not just the destination, it is the path with all of you together. Thank you.
Uh-oh. Now I have to like wrap this up. Okay, do we have any announcements or anything, Janice? No. Lunch is served. Okay, so thank you, everybody. I'll say on behalf of Hopkins, I am like so excited this happened here, and I can't wait to see what happens next. Everybody go have lunch, and don't forget about dessert.